All right, let's go through everything there is to know about sequences and series in one unbroken take. First off, let's talk about sequences here. So a sequence is an ordered list of numbers, and that it's an ordered list is the most important part here, written as these little curly braces, a sub n, where n is a positive integer. Okay, so it's just an ordered list of numbers. That is, it will look like a1, then a2, then a3, and so on and so forth. That is, for example, it could look like 2, 3, 4, 6, 8, so on and so forth. Keep in mind that this thing right here, the dot, 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 anywhere that you see it, means that it is infinite. Now, let's switch over to a nice little blue, and let's look at an example here. So, given a sub n equals 2n minus 1. Let's write the first 5 terms of the sequence. So it looks like this. We're going to plug in n equals 1, 2, 3, 4, 5 to this. First we're going to plug in 1, then 2, then 3, then 4, then 5. So we're going to get something that looks like this. Our a sub 1 is going to be 2 times 1 minus 1. Okay, 2 times 1 minus 1 is, well, 1. Our a sub 2 will be 2 times 2 minus 1, which will equal 3. Our a sub 3 will be 2 times 3 minus 1, which will equal 5. Okay, by the same logic, by plugging in 4 and 5, we'll get that a sub 4 is 7, and I'll put a semicolon here, a sub 5 is 9. That is, the first few terms would look like this. We would have our sequence, an, so that means an, these little curly things mean a sequence, and that just is a set. It's the same thing that a set's always meant. It's 1, 3, 5, 7, 9, so on and so forth. So that's the first 5 terms of a sequence. Now, if a sub n is negative 1 to the n over n, well, I want to write the first 5 terms of that. It's the same thing. I'm going to plug in, this right here just means plug in, n equals 1, 2, 3, 4, 5. So I'm going to do that. This thing right here has a special name. It's called an alternator. And you'll see why in just a second. So it works like this. The first term, and I'm just going to write the whole thing out like this. I'm going to write the first few terms of a sub n out like this. So watch this. A sub n is, okay, it's the set containing, well, negative 1 to the 1 over 1. And then the next term is negative 1 to the second power over 2. The next term is negative 1 to the third power over 3. The next one is negative 1 to the fourth power over 4. And then we'll have negative 1 to the fifth power over 5. And it will continue indefinitely because it is an infinite sequence. Let's make our pen a little smaller here. And then let's actually evaluate each one of those terms. So, negative 1 to the first power is negative 1 times itself. Well, that's it. It's just negative 1. So this will be negative 1, well, over 1. So that's it. Negative 1 over 1 is just negative 1. Negative 1 squared, so if you raise a negative number to a positive power, you will get a positive number. So you get a positive 1/2. Then you'll get a negative 1/3. Then you'll get a positive 1 over 4. Then a negative 1 over 5. And so, that negative 1 to the n guy up there, this guy right here, is called an alternator because the signs, look at this, let's go grab an orange, because look here, they alternate. Positive, negative, then that's positive, that's negative, that's positive, that's negative, the next term will be positive, and so on and so forth. So that's how that works. Okay? Let's move on. A sequence defined directly in terms of n, such as a sub n equals f of n, is called explicit. It's an explicit formula, or you can say, if you want, that it has a closed form. So you can also write that, a closed form formula. Okay, so A3, A5, and A10 for A sub n equals this. That is, we have the sequence that looks like, that's a curly brace, n squared plus 1 over 2n. Well, that's just some function, and it's always worked like it's always worked. So those functions, this function inside is going to work just like it's always worked. So if you want the entire function, plug in n equals 1, 2, 3, 4, 5, 6, 7, whenever you want to stop. This problem specifically asks us to find, for instance, a sub 3. Well, a sub 3 is going to be, I'm going to plug in 3 to everything. A sub 3 is going to be 3 squared plus 1 over 2 times 3. Okay? And that's going to be it for that. Well, if you plug all of that in and you do all the math on that, you're going to get, let's see here, you're going to get, I believe, 5/3. Yes, 5/3. You're going to get equals 5/3. Okay? If I want to do a sub 5, which is the next one, well, that's 3, that's not 3, that's 5 squared plus 1. Let's put a line here so we can, that's 5 squared plus 1 over 2 times 5. Over 2 times 5. You do the math on that. You're going to get 25 plus 1 over 10, which is 26 over 10, which is 13 fifths. I'll let you do the math on that. We're in a Cal 2 class. And then let's do a sub 10. A sub 10 is, you're not going to believe this, 10 squared plus 1 over, we're going to do 2 times 10. And you do all the math on that, you'll get 100 plus 1 over 20, or 101 over 20. So those are those different terms. And that's it. That's all there is on that. So let's just continue on. Let's evaluate a sub 4 and a sub 8 for this one. Now, throughout these videos, I urge you, please pause the video, write this down, try it. That's the only way you're going to learn things, is to try to go through and do these things on your own. So, pause the video and try it. If I've already done an example, then when I do the second example, just pause the video and try it. I'll probably say that repeatedly, but at some point I'm going to stop saying it and I'm just going to keep working through these. You can mindlessly watch me do every single one of these, but unless you're actually trying to write them down and figure it out before I do it, there's not really any value. The pause button is your best friend in all of this. So let's find A4 and A8 for these. So we're going to plug in n equals 4 to this. So a sub 4, so that is the fourth term, or the fifth term if you start with 0, is going to be negative 1 to the 4 plus 1 times 3 over 4. So when we plug all that in and we do all that, we're going to get a negative, because that's negative 1 to the 5th, that's negative 1 to an odd power, so the alternator's negative, times 3/4, which is, well, 3/4, right? And then a sub 8, of course, is going to be the same sort of thing. It's going to be negative 1 to the 8 plus 1 times 3 over 8, which is going to give us, of course, negative 3/8. Okay. If you wanted to write out the sequence explicitly with that closed form, with that explicit form, you would just start with 1 and plug in 1, then plug in 2, then plug in 3, and that will be all the sort of things. All right. Now, we can plot graphs of sequences. Okay. So we can visualize them as discrete points n, comma, a sub n in the plane. And so let's plot, for example, the first 5 terms of a sub n equals 1 over n. So we know, of course, the first 5 terms will be a1, a2, a3, a4, and a5. And I don't want to belabor this point, so we won't do too many of these. But it's worth looking at a few of these. Just like this, just like this. Okay, so a sub 1 will be 1 over 1, which is 1. A sub 2 will be 1 over 2. A sub 3 will be 1 over 3. A sub 4 will be 1 over 4. A sub 5 will be 1 over 5. And then we could just keep continuing forever on that way. Now, if you, if you graph these in a plane, we'll be able to do something like this. Okay? Now, I need, on the x-axis, I just need our n's. So that is 1, 2, 3, 4, 5. So I'm going to do 1, I'm going to do 2, I'm going to do 3. I'm going to try to space them out equally here. 4 and 5. There we go. 1, 2, 3, 4, 5. Okay. And then I'm going to do 1. I need to do 1. A half is half of that. And then a third is a third of that. And then a fourth. And then a fifth. Something like that. And it's going to look something like, there's a sub 1. Okay. Here's a sub 2. Here's a sub 3. Here's a sub 4. I'm just going to the place where these things meet. Here's a sub 5. And so, if I go up here and grab orange, and I come through here, here is the graph. Okay? And it seems to be trending down asymptotically towards the x-axis, which is what you would expect. It behaves, amazingly, like a function, just so that you can look at it. So, we don't look at that very much, but a sequence can be visualized as discrete points. You just label 1 through whatever on your x-axis, and then your y-axis is whatever it evaluates to at that point, and then you can look through it. So sometimes that's useful. Maybe it's much easier for you to see the thing on the right than the thing on the left, that they're both going to 0. But that does take me back towards the limit of a sequence. If the terms of a sequence approach a number L as n goes to infinity, then the limit as n goes to infinity of that sequence's closed form expression, like 1 over n in the last example, equals L. And we say the sequence, we also say that the sequence, and we can say, and the sequence, okay, converges to L. Now, we don't always know what sequences converge to, but knowing that they converge helps. So we want to evaluate the limit as n goes to infinity of 1 over n. So we're in a discrete space right now, but we're using a continuous operator. That is, we're in a discrete space. N is counted 1, 2, 3, 4, 5, 6. But this limit here allows for just about anything. The good news is this works just like everything you learned in Cal 1. You know that limit should go to 0. Because the top is not changing, and the bottom is changing and getting bigger, then 1 over a bigger and bigger number is a smaller and smaller number, and it's 0. That is, L is 0 in this case. All of the tools that you've ever learned tell you the same sort of thing. This guy right here, you can use L'Hopital on this if you want. Same sort of thing, right? Just change it to X and use L'Hopital on it if you want. Right? You can look at the limit as n goes to infinity of 2n over 5 if you want. Or if you really want to do it, you can divide each term in the numerator by n, and you can get the whole thing out and look at it like this. So that is, you can look at this as, instead of 2n plus 5 over n, you can look at it as 2n over n plus 5 over n, which is, these cancel. So this is 2 plus 5 over n. And of course, taking the limit as n goes to infinity of 2n plus 5 is the same thing as taking the limit as n goes to infinity of 2 plus 5 over n. And of course, you know, as n gets infinitely large, this term goes to 0. So then the limit is 2. That's the whole thing. Okay. So this entire limit is just 2. As it turns out. Now, of course, we know that we can also just look at this, and we can look at just the dominating terms, which I'll do in orange here. The dominating terms are the highest degree terms in the numerator and the denominator, so we can look at just 2n over n. This 5, as n gets infinitely large, this 5 is inconsequential. We can look at just 2n over n, the n's cancel, and you get 2. You can look at it that same sort of way, but if you're not comfortable, then we've written down what we need to write down there. The next example here is to evaluate the limit as n goes to infinity of 3n squared plus 1 over 2n squared minus 4. It's the same sort of idea. You can look at this. N is getting infinitely large here. So then this plus 1 and this minus 4 don't really matter. And look here, the n squareds cancel, and what you're left with is 3 over 2. If you want to, you're more than welcome to pause and divide the numerator and denominator by n squared. You'll get 3 plus 1 over n squared over 2 minus 4 over n squared. You'll see that those things go to 0. It's the exact same logic. But really, that logic works in all of these sort of things. You'll see here in example 9 as well that these things are going to look to be jumping back and forth. If you want to look at the terms of this, the terms of this right here, this guy right here, if this is your a sub n, if this is your sequence a sub n, then your terms in a sub n are going to look like negative 1, 1/2, negative 1/3. We did this earlier. Positive 1/4, negative 1/5, right, and so on. And we start to get to this idea of absolute convergence that we're going to come back to in series. It isn't quite what it is right now, but you can see that while they are jumping back and forth between negative number, positive number, negative number, positive number, negative number, positive number, if you would like to pause and graph these, you'll see that they are bouncing back and forth, but they're bouncing back and forth towards 0. And what we can just do is we can look at the absolute value of a sub n and see what they're doing in absolute value and get some information off of that. So in absolute value, well, this is just 1 over n. And we know that that goes to 0 as n goes to infinity. So we can look at it that way. But if you look at an x-axis and a y-axis here, something like this, you're going to see your numbers. Well, we started with negative 1. So you're going to see your numbers start here, and then we'll go over another one, and it'll be a little closer, and then a little closer, and then a little closer. And they're kind of doing something like this. So you get the idea that while they're bouncing back and forth, they are getting closer and closer to 0, is the kind of thing that we're looking at. So that's the general idea in that. But this is the first time that you actually see the idea of looking at something in terms of its magnitude. And when I say its magnitude, I just mean slap some absolute value signs and look around it. Which all this does is it just brings all these negative points, their corresponding distance up here, and basically just fills in the gap and lets you look at it that way. Completely valid way to look at mathematics, by the way. Here we want to look at the limit as n goes to infinity of 1 plus 1 over n to the n, and we actually should know that this is literally the definition of Euler's constant E, that 2.71 guy that keeps showing up. This shows up over and over in finance. It's one of the fundamental limits that is worth remembering. If you want to keep plugging this in, plug in n equals 1, 2, 3, 4, 5, 6, 7, 8, 9 in a table, and you'll see that the numbers that you get out keep getting closer and closer to Euler's constant E. That's all that there is to that one. Now, we can talk about convergent and divergent sequences. So I previewed this earlier, but a sequence is convergent if it has a finite limit. That is, if it ends up equaling a number, it's convergent. That means it converges to a number. You don't have to know what the number is. You just have to know that it will converge to something. If it does anything else, that is, it goes to positive or negative infinity, or it's just not a number, or any other weird thing that can happen in math, it's what we call divergent. Determining convergence and divergence of sequences and series is the only thing that we're doing for the rest of this entire chapter. That is the rest of this video. We're just looking at convergence and divergence. We're going to do a little bit first in sequences before we move on. However, we're just going to be looking at convergence and divergence overall. So we want to know whether a sub n equals 5n over n plus 1 converges or diverges. I'll tell you right now it converges. I know it will because I know that this is going to equal a number. How do I know that? Because it has to do with its limit, if it has a finite limit. So we're always looking at the limit. I want to look at the limit as n goes to infinity, which is always what we're looking at, of 5n over n plus 1. Well, remember, in the limit, we only care about the highest degree terms like that. We only care about the 5n term, because that's degree 1, and this n term here. This guy doesn't actually end up mattering when we get bigger and bigger. Those cancel, the limit is 5. Okay? Now, if you want to do this mathematically, instead of that weird way, then we can look at the limit as n approaches infinity, okay, of 5n over n plus 1. Okay, we can divide everything top and bottom. I'm just going to copy this. We can divide everything top and bottom by n. So 5n divided by n is 5. Okay, and then I get n divided by n is 1, plus 1 divided by n is 1 over n. Okay, and then as n goes to infinity, this term vanishes. We get 5 over 1, which is 5, which is the same thing that we said. It converges because this guy's a number. Okay, it goes to something. It's some real number. By the way, it could also be a complex number, and depending on what it is that we're working with, it might be fine. Now, in the case of series and sequences that we're working with right now, we're usually looking for real numbers, but as long as we get something out of it, we're good to go. All right? As long as it makes sense in the context. So in the normal context of things, we're just counting things. So we usually want real numbers. Was this a real number? 5? Yeah. So then it's convergent. What if it had been the square root of 5? Cool. Still convergent. 12? Still convergent. 7.22 repeating? Still convergent. Square root of pi times e? Doesn't matter. Still convergent. Those are all numbers. That's all we're looking for. Okay. I want to know whether the alternator converges or diverges. Okay, let's look at whether the alternator converges or diverges. So, look here. I want to know the limit as n approaches infinity of -1 to the n. So does this ever settle on a number? Can we look at that? Does this ever settle on a number? Because the sequence is going to look like -1, 1, -1, 1, -1, and so on forever. That's what the sequence is going to look like. So does it ever settle on a number? It does not. Since it doesn't, we say that this limit does not exist, and therefore it's not a number, so it diverges. That's it on that one. How about the natural log of n? Does that converge or diverge? Then we look at the limit, because that's what it has to do with. The limit as n goes to infinity of the natural log of n. Okay? As n goes to infinity of that, we know that this goes to infinity. It goes to infinity extremely slowly, and the quote-unquote closer it gets to infinity, the slower it goes, but it does grow without bound. And since infinity is not a number, it diverges. The only way that it converges is if you get a number out in the limit. Okay? Now, that idea of boundedness from the last problem takes us to this definition. A sequence is bounded if there's some number that the sequence is always smaller than, no matter what number you put in. That should make sense. There's some upper bound or lower bound. That means that it's bounded. Cool. And then a sequence is said to be monotone increasing if every number after the last one is bigger, and it's monotone decreasing if every number after the previous number is smaller. So let's determine whether this is bounded, and let's determine whether this is monotonic. And I want to go back to blue because I prefer it. Okay, let's look at that. So let's look at the a sub n equals 1 over n. So let's remember that that looks like 1 over 1, 1 over 2, 1 over 3, 1 over 4, so on and so forth. Okay, is that bounded? So is there some m such that that's either the biggest or the smallest it can get? Okay, is there some m that works for that? That all of the terms in absolute value are between it. That is, this literally means it's between negative m, the terms are between negative m and positive m. Is there a number that I can pick that does that? Well, yeah, 32,000. None of these terms are ever going to be bigger than 32,000, nor are they ever going to be smaller than negative 32,000. I'm not saying anything about m being the least bound, the least upper bound, or the greatest lower bound. We don't care about that. It's just, is there a number? Yeah, 30,000. In this case, the actual number is 1. every number in this sequence is between plus or minus 1. Because it never gets smaller than 0, so those are all definitely bigger than negative 1, and it never gets bigger than 1. That's as big as it'll ever get. So in this case, we actually know what m is. M is 1. And m is said to be the least upper bound. The greatest lower bound, by the way, is 0, but that doesn't work for both of them. So yeah, it's bounded. And then the other question is it monotonic? Yes, this is monotonic. Specifically, it's monotonically decreasing, because as the numbers go this way, they're getting smaller. And at no point are they ever going to just hop up for a little while and then die off again. They're always going to keep getting smaller forever. So let's look at another example down here. Determine whether a sub n equals n squared is bounded and monotonic. That's an easy enough one. Let's look at that. Is it bounded and monotonic? So remember, the numbers are going to look like 1 squared, right? 2 squared, 3 squared, 4 squared, 5 squared, and so on. Okay, that's the sequence, n squared. That's what it looks like. Okay. Is it bounded and monotonic? Is there a number that I can pick that will never get bigger than and also at the same time smaller than? Well, you might think 1, but we get bigger than 1 immediately. In fact, you know that there is no m. It doesn't matter if I pick the number 32,392,912. At some point, if I keep listing out all the squares as I go this way, I'm going to get a number bigger than that at some point. Indeed, for any m that you pick, if I give you back m squared is guaranteed to be in this set, so it certainly won't work. Puzzle that one out for a second if you want. But, so it's not bounded. We know that. It grows without bound, we would say. But it is monotonic. That is, it's monotonically increasing. The numbers are going up. The numbers are going up as we read them from left to right. The numbers are going up. In fact, if you graphed these, it would look something like that. Right? So think about that. So it is monotonic. It's said to be monotonically increasing. However, it's not bounded. Neat. Okay, we're going to look at the monotone convergence idea in a second because that's a cool one. However, determine whether the alternator is bounded and monotonic. It is not monotonic. Remember, this is the sequence -1, 1, -1, 1, so on and so forth, like that. It's not monotonic. It jumps up and then down and then up and then down and then up and then down and then up and then down. So it's not always decreasing or always increasing. So that's not the case. But there is an m equals 1 again, by the way, such that every term in a sub n is less than or equal to 1. That is, every term, you pick one. It doesn't matter. It's going to be true for all of them. It's going to be between -1 and 1. That's true. By the way, it's also bounded by 72 billion. Because every single term in this sequence is between positive and negative 72 billion. Because we're only talking about boundedness. And that's a very important idea to keep in the back of your mind, by the way, what boundedness means. It just means you can pick a number. That's all that it says. Okay? Now, why do we spend so much time talking about that? Well, if you've already read below, you'll see there's this thing called the monotone convergence theorem, and it's really more of an idea to me. But it says that a sequence, any sequence that's both bounded and monotone, is guaranteed to converge. Think about that. It's got bounds on it, and it's only increasing or decreasing. So if you think about anything that's bounded and monotone, something that looks like this, right? It's always increasing, but there is some upper bound that it's headed towards. Some upper bound that it's headed towards. Because it's monotone, we know that it's always going to increase, right? So it's never going to do this. Because it started increasing, it has to keep increasing. Same thing, by the way, for the orange up here. If it's always decreasing, okay, but it's bounded by the blue line also, then at some point it has to converge. It has to converge to the blue line, right? That's how that is. So we want to know whether this, just based on monotonicity and boundedness, is going to converge or not. Well, then let's think about that. Okay? Let's look at this. Let's look at this guy right here, as instead of n over n plus 1, okay, let's notice that this is the exact same thing as, so that is our a sub n. Okay, if you want to do some math on this, n over n plus 1, we can rewrite this as 1 minus 1 over n plus 1. Okay, go back to algebra if you want to figure out how that's done, but we can look at that like this. Okay, we know that this guy right here, we know that that guy right there is greater than 0. That'll always be greater than 0. Then we know that our a sub n, okay, is going to have to be less than 1. It will always be less than 1. And indeed, you can list out the terms here and see that pretty clearly, right? Your first term is a half, then a third. Sorry, not a half, then a third. A half, then 2/3, then 3/4, then 4/5, 5/6, and so on. So clearly that's getting closer to 1. We're less than 1 on that. But we also know that these things, as n increases, that this 1 over n plus 1, this term here, this term right here, down here, this term decreases, right? Which means that the whole thing is going to increase. So the sequence is increasing. We can see that the sequence is increasing clearly. Type those into a calculator if you don't believe me. So it's increasing, and then at the end of infinity, quote unquote, there's a 1, right? So it's bounded by 1. It's bounded by 1 somewhere all the way up here at the end of all of this. It never gets there, of course, but that's the idea. Well, then we know that its limit is 1, but we also know that it has to converge. We know that the limit is 1, by the way. That's the easiest way to tell. Okay. And if you want to go back to the old thing, divide each term by n, you'll get 1 over 1 plus 1 over n. You'll see that the whole thing goes to 1, therefore it converges, yada yada, that's the whole thing. Or you can look at it like, well, this plus 1 isn't actually doing anything in the denominator. Those cancel. Sorry. Those cancel right there. Those guys cancel, and you get a 1 out. That's fine. But that's the idea between monotonicity and boundedness, and it really is just that first graph that I drew there. So this idea really is exemplified here just by this guy here. If you're always decreasing, but you're decreasing towards a bound, then you're converging to the bound. If you're always increasing and you're increasing towards a bound, then you're going to converge to the bound by the same logic. Now, let's move on to the meat of this, and let's talk about infinite series. But before we get to series, we need to remember how sigma notation works. So this guy right here is the capital Greek letter sigma. Okay, and you've got the guy here called the index. That's the n. Okay, then you've got your limits of your index. You start here and you end here. And then you've got what's called the summand, S-U-M-M-A-N-D. That's the thing that you're summing over. And you're said to be summing over the summand. That's just how you write it. So we could write the sum of all the even numbers, well, like this. We're going to add together all of the even numbers, and you start with, you choose where to start. I usually start with 1. We're going to go forever. Of course, that's what the ... means. We're going to go forever. Okay. And then what does an even number look like? Well, it's a number that's divisible by 2, right? So that means it's 2 times some number. So 2n. That's it. That will give me exactly 2 times 1, that's the first term, and then we do 2 times 2, the next term, and then we do 2 times 3, the next term, and then we keep going on forever, right? And so that is, of course, exactly 2 plus 4 plus 6 plus so on and so forth. So that's how that works. So let's write this guy here in expanded form just for a little bit of practice. Again, pause if you need it, but in expanded form, we would write this guy right here as, we'll just say equals. So this guy right here, and the less compact way to write it is like this. Right? This is called inline, by the way. This is how you write it if you're trying to keep it in one line. We have more lines than that, so we can write it like this. N squared plus 1, okay, like that. Then this is going to be, well, 1 squared plus 1 plus 2 squared plus 1 plus 3, in parentheses, 3 squared plus 1 plus, in parentheses, 4 squared plus 1 plus, in parentheses, 5 squared plus 1. That's it. So what is this? Well, 1 squared plus 1, 2 squared plus 1, 3 squared plus 1, 4 squared plus 1, and 5 squared plus 1, we all just do, right? And we get 2 plus 5 plus 10 plus 17 plus 26, okay? And all it says is write it in expanded form, and that's fine. If you want to find what the first 5 terms of this equal up to, we'll just add those things together. But that's the first 5 terms. That's all that we really wanted, okay? An infinite series is a sum of the terms of a sequence like this. That is, we're just going to add together the terms of a sequence. So everything that we just learned. It's infinite because it goes on forever instead of ending with a bound. This had 5 terms in it. This guy down here has an infinite number of terms in it. Okay, so write out the first 5 terms of that. Of course, the first 5 terms of that are just going to look like 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 and 1 over 5. Those are the first 5 terms. Specifically, the first 5 terms are the terms in the sequence. 1, a half, a third, a fourth, and a fifth. That's it. But yes, you just add them together. That's it. You just add them together. And I should have added this as well. So plus 1 over 5, like that. That's it. So it keeps going though. Plus dot dot dot. That's important to remember. So the sum from n equals 1 to infinity of 1 over n. That's called the harmonic series. We'll talk about that more in a second. It does not converge because it's really slowly diverging. That's basically the reason, but we'll get to that in a minute. We still want to write out the first few terms of these. So here's something kind of complicated. We want to write out the first 4 terms of this. So we just need to figure out what the first 4 terms of this are and then add them together. Something to be very careful of on this is where the index starts at. Okay? So the index on this actually starts at 0. So the first term is going to be a sub 0, and then we're going to do a sub 1, a sub 2, and a sub 3, and that'll be 4 total terms. Okay? Keep that in mind. Okay? So the first thing here is going to be negative 1 to the 0, 2 over 0 plus 1. This is very common in computer science to start with 0, by the way. And we'll get out of that, of course, just 2. Okay? And then you do the same thing in each one of these. You plug in whatever it is you're dealing with. So 1 is the thing that we're plugging in with this. We'll get out negative 1 when you do all of the math in this. You can do all of the math for a sub 2. You'll see that you get 2/3. For a sub 3, you'll see that you get negative 1/2. Please, by all means, go do all the math on this. So then our first 4 terms, our sigma n equals 0, careful, to infinity, of the alternator 2 over n plus 1. Well, that's just going to equal 2 minus 1 plus 2/3 minus a half. And then anytime we're ever going to write a dot dot dot, whether we know the next term is going to be positive or negative, we just write plus as convention. That is, if we had stopped writing the series here and we just hadn't written that A3 term, we would still write plus dot dot dot. You don't write minus dot dot dot. That's just not convention. You always write plus dot dot dot. Just keep that in mind. But that isn't where we were headed with that. So that's something to keep in mind with that. Okay, let's look at partial sums. So a partial sum of a series is, first off, a series is just an infinite sum, and a partial sum is you just add up to whatever that number is. Okay, this is super easy to understand once you've done a few of them. It looks really complicated, but it isn't. So remember, the terms here are s sub 1. Okay, so that's just the first term. Okay, and when you see something written with a series like this, by the way, just series 1 over n and there's nothing written, it always means n equals 1 to infinity. So if nothing's written, that's what it means. Okay? But S sub 1 is just the first term. Okay? So, I'm sorry, 1 over 1. Okay? S sub 2 is going to be the first two terms added together. 1 over 1 plus 1 over 2. S sub 3 is 1 over 1 plus 1 over 2 plus 1 over 3. Okay? And then S sub 4, you're not going to believe this, guys, is 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4. Now, you want to do the god-awful math on all of this. Obviously, that's just 1. Okay? That's 3 halves. I'm okay with that. You do the math on this, you'll get 11 sixths. And then if you do the math on this, you'll get 25 twelfths. Okay? So that's it. S1 is 1, S2 is 3 halves, S3 is 11 sixths, and S4 is 25 twelfths. Please notice that S sub 1 does not happens to mean the first term, but S sub 2 is not just the second term S 1 half. It's not. It's you add together the first this many terms. You add together the first this many terms. You add together the first this many terms. Right? It is not that term in the sequence. Completely different. That is a rookie mistake that everybody's going to make at least once, but that's how that works. So, try this. Find the first 4 partial sums of that guy. Please pause the video. Again, the pause is your best friend, and give that a shot. So we know then that S1 must be 1 over 2 to the first. S sub 2 must be 1 over 2 to the first plus 1 over 2 squared. S sub 3 must be 1 over 2 to the first plus 1 over 2 squared plus 1 over 2 cubed. And then S sub 4 must be all of this stuff plus the next term. So 1 over 2 to the first, that's not a 3, plus 1 over 2 squared plus 1 over 2 cubed plus 1 over 2 to the fourth. Okay, well, what are those? Well, let's figure out what all those are. This is, if you do the math on all these, this is 3/4. You'll get 7/8 on this one. You'll get 15/16 on this one. Okay. You'll get 15/16 on that one. So, cool. That's neat. Those are the first 4 terms. By the way, a series converges if the limit of the sequence of partial sums has a finite end. That is, if it converges. So, a series converges if and only if the limit of the sequence of partial sums also converges. So we can actually look real quickly back at this one and see that it converges. Because look at the limit of its sequence of partial sums. Imagine a sequence where that's the first number, that's the second, that's the third, that's the fourth. That's clearly going to 1 pretty quickly too. Since that converges, then this series converges. And in fact, we can even say, can we say that this equals 1? Well, yeah, we can. We can actually say that that equals 1. Now, it's a little bit more complicated than that. This thing's called a geometric series, but yeah, that's exactly right. So, well, it's a strangely written geometric series. This needs to be -1 for it technically to be 1, but you can rewrite it a little bit differently. Yeah, this does end up equal 1 because of this down here. This next example is determine whether this series converges or diverges. This series, by the way, just equals 1 plus 1 plus 1 plus 1 plus ... forever. Okay? What is its sequence of partial sums? Well, its sequence of partial sums will be 1, and then 1 plus 1, and then 1 plus 1 plus 1, and then 1 plus 1 plus 1 plus 1, on forever, and that clearly goes to infinity. So that diverges, therefore this guy will diverge as well. If you add 1 to itself for forever, you're not going to get a finite number out of it. Something to remember about series convergence is we don't always know what the series converges to, but we do know that it's going to equal something, some number, but we don't always really have to care about what it equals. And that's cool because oftentimes we can't know that. So let's determine whether this converges or diverges. So this is a fun one. This guy is called the harmonic series. Okay. Now, this diverges. Okay. First off, this guy's called the harmonic series. This is called the harmonic series. Okay. And it diverges. Okay. This is a standard series. It's one that you just need to memorize that it diverges. I urge you, pause the video, go look up why does the harmonic series diverge. You'll find 300 different examples of them and of why that is the case, and 150 of them will make some sense to you and the rest will be complete garbage, which is why I'm not going to go through exactly why it does here. The point is, as I said a little earlier, that the harmonic series does get less and less the more you go on. You're adding a little bit less the further you go on. Every subsequent term is just a little bit less than the previous one. But it doesn't get less enough fast enough for the total thing to actually equal something. That is, when you add 1 plus 1/2 plus a third plus a fourth plus a fifth, on and on forever, you don't get some finite number out. But you do get a finite number out for the geometric series, which is something that we're going to look at here. And I want you to think really, really carefully about this right here. And I want to actually give you the proof for the geometric series, and then we'll do this thing here. So for just a moment, I want to go over the basics of this. I want you to just see the text on the screen like it's in some language you don't speak, which might be funny because math's hard sometimes, right? But just think about it as the entire screen, right? So I'm going to ask you a question, and I hope that I can undo far enough. Otherwise, we're just going to have to skip this. But imagine that I divide this in half. Okay, very bad division in half because this tablet is really hard to work with. But this over here is 1/2 of the screen, right? Now, if I divide this in half again, this is 1/4 of the screen, right? Remember, this whole area here, everything on the screen is one screen, right? Now, if I divide this in half again, wow. If I divide this in half again, okay, this is now 1/8 of the screen, and I can divide it in half again, and this will be 1/16 of the screen, okay? And then I can divide this in half again, and so pretend like that was exactly in half. That'll be 1/32 of the screen, and then this is 1/64 of the screen, okay? And then I can keep doing this on and on forever. And imagine when I get to about this, that I just really zoom in to the top right-hand corner here until it is its entire own screen again. And then I can do this process over and over and over, right? Clearly I could do that forever, assuming I can zoom in, which mathematically, of course, we can. Because the real numbers are dense. So the question is how much of the screen is there? How many screens are you looking at with your face right now? Well, you're looking at one screen. But my question is, what is 1/2 of a screen plus 1/4 of a screen plus 1/8 of a screen plus 1/16 plus 1/32 plus 1/64 plus 128th plus 1/256 plus 1/512 plus 1/24th and so on, 1/1024th and so on and so forth. Forever. What is that? It's one. It's one whole screen. You're looking at one screen. And yeah, I've divided it into half and then half a half and half of half of half and so on and so forth. But you're still just looking at one screen, okay? Now, I'm going to try to rewind this back as far as the undo will let me in memory. And I have no idea if this works or not. I hope I can undo the whole thing. It's looking promising and cool. I can do that. Then we can say that if you add those numbers together, which by the way, 1/2, 1/4, 1/8, and so on, look like this. We just looked at that. So if you sum these, starting with 1/2, so 1/2 to the first, on and so forth, we say that that converges to 1. Okay? That's what we just showed. That's a geometric series. It's called a geometric series because I just use shapes to explain it to you. I swear that's all it is. There's a geometric reason for why it looks like. But we can generalize them. They look like this. A to the R, A times R to the N equals 1 to 0. You sometimes also see this And if you use the OpenStax textbook, you see that it looks like this, n equals 1 to infinity of a r to the n minus 1. That's also true. So it just depends on which version you want to use. So look at your index to see whether or not n is n or n is n minus 1. It just depends. These are equivalent. They're the same thing. If you don't believe me, convince yourself. Just write out all the terms. It converges if r in absolute value is less than negative 1. And remember what that means is that r is strictly between positive 1 and negative 1. What that actually means is that r is a positive or negative proper fraction, including 0. That is, the numerator is strictly smaller than the denominator. Positive or negative, it doesn't matter. If that is what r is, then it will converge, otherwise it diverges. And in fact, we can say if it converges to a divided by 1 minus r. So that's cool. So we can look at example 26 here, and we can see that a must be 5. That's an a, believe me. Let's try that again. Let's just try that again. A is 5, okay? And then we know that r must be 2/3. Now, we're good to go on this. Even though this is n equals 0, so that's one of the forms that could have worked. If n was 1, then we would need this to be n minus 1 to work. So be careful on that, but we're good here. Okay. And since that's the case, our question is 2/3 in absolute value less than 1? Yes, it is. Clearly it is. Okay, it's a proper fraction. Then its sum is going to be a over 1 minus r, okay, which is just going to be 5 over 1 minus 2/3, okay, which is 5 over 1/3, which is 15. So its sum is 15. So this is an infinite series. This is cool. This is an infinite series. You can add together an infinite number of terms and get a finite thing out. We can turn the infinite into the finite. That is an insanely powerful tool, and it's used all the time in engineering. All right, learning how to do this convergence or divergence lets you know whether or not you can even do the problem that you're trying to get to first. There's tons of practical uses for this, but everything that we're doing here is a practical check on whether or not you should waste what is going to be an extremely long amount of time figuring out your next steps. Maybe you can save yourself a lot of trouble and figure out, oh, that diverges. I don't need to work on that. Okay? Let's do a couple more of these. Okay? So this is, look here, this is one of these that's going to get you. Okay? This goes from n equals 1 to infinity, 3 times 2 to the n. I want to know whether or not that converges or diverges. Okay? Now, we know that this is going to diverge because r equals 2. But this isn't actually written like a geometric series needs to be written. Because remember, if you've got an n up here, you need to start at 0. If you start at 1, then you need to have an n minus 1 up here. But we can write that as n minus 1 and be okay. So we can look at this and we can say n equals 1 to infinity of 3 times, I want to write this as 2 to the n minus 1, and I can do that by just, well, pulling out a 2. Right? You have n minus 1 2's here. That's what 2 to the n minus 1 means. It means you're going to multiply 2 times itself, n minus 1 times, and then there's the other one. So what this actually is, is that this is a geometric series, n equals 1 to infinity, with a equals 6 and r equal to 2. Okay then. But in that case, r equals 2, right, which you'll notice is greater than 1, so then this thing diverges. Because remember, all you want to know is the thing that you're raising to an exponent a proper fraction? If it is, it converges, otherwise it diverges. Well, clearly 2 divided by 1 is not a proper fraction. The top, the numerator, is bigger than the bottom. Bigger than or equal to the bottom. So, there you go. I want to rewrite this bad boy right here, in the next example, as a standard geometric series. So it actually starts at n equals 2. So there's 2 different ways that we can do it. We can write it back at 0, or we can write it back at 1. And it depends on which way you want to do it. Now, what we can do then is we can just say, okay, well, I need this up here to just be some exponent by itself. If we want to start with n equals 0, then this just needs to be some exponent by itself. Then just let k, I'll just say let k equals n minus 2. Okay? If k is n minus 2, then n is k plus 2. Right? N is k plus 2. But we can also say that when n equals 2, k equals 0. We can also use this here to say when n equals 2, k equals 0. That's true, right? Which means that this series can be rewritten as, we can start with k equals 0 to infinity still, okay, of 4 times 1/3 to the k. Because remember, when n equals 2, which is what I started as, k equals 0, so n equals 2 becomes k equals 0. So our n equals 2 became k equals 0. And then our n minus 2 became k. So there we go. We wrote that as a standard geometric series. This, by the way, is called index shifting, because we just shifted our index around. Right? So that's what we're trying to do on this. That's all that we're doing on this. Now, let's talk about a telescoping series really quick. These are cool. Telescoping series are really cool because they let us see that a telescoping series is just a term that cancels on successive partial sums. That's cool. If we write out the first 4 partial sums of this, you'll see what I mean by this. Okay? And I don't actually want to do this. I can show you. Let's just look at the 4th. Okay. Let's look at the 4th partial sum of this instead. That is, let's just look at s sub 4. Okay? So that's going to be 1 over 4 minus 1 over 5. Okay? Okay? Plus, and then the next term will be 1 over 5 minus 1 over 6 plus 1 over 6 minus 1 over 7 plus 1 over 7 minus 1 over 8. Okay? And then these pluses aren't really doing anything, so you can just delete them in your mind's eye, and you'll see, hey, look, minus a 5th plus a 5th, minus a 6th plus a 6th, minus a 7th plus a 7th. So then this is just 1/4 minus 1/8, which is an 1/8. That's it. Okay? So that's the sort of thing that I looked at. Now, you may be asking, why did I start with 4? And the answer is, because I'm silly. I should have started with 1 here, but it's the same sort of point. Okay? So it's the same sort of point. You're going to see the same sort of cancellation no matter what you do. All right? But this isn't actually s sub 4. That's my bad. I started with 4 because I saw the 4 here and I got confused. But you would start with 1 over 1 minus 1 over 2 plus 1/2 minus 1/3 plus 1/3 minus 1/4 plus 1/4 minus 1/5, and you would get the same thing. All the same terms would cancel, and you'd have 1 minus 1/5, which would give you 4/5. Same sort of thing. I just made a little brain fart there. That's okay. It's the same sort of thing. So I'll show you a little bit better here in example 31. Remember, I'm doing all of this in one very long take. So I have been teaching for nigh on an hour now. So let's look at this and see if I can write on this first. Okay, cool. So we can use partial fractions to rewrite this. Okay, so you can use partial fractions. It's the same thing from partial fraction decomposition. You can use partial fractions to rewrite this, and you'll realize that it'll rewrite really nicely. If you want to go do the partial fractions on it, go do the partial fractions on it. Pretend like you're trying to find the integral of this. But you'll get 1 over n minus 1 over n plus 1. Okay. And then you'll notice that everything is going to cancel as you add these terms together. Okay. That is, the terms are going to look like 1 over 1. So 1 minus a half plus a half minus a third plus a third minus a fourth minus a fourth. And this is just going to keep going on and on forever. Okay. So plus dot dot dot. Right. I'm just doing this series here. So this equals this. Right. I'm just doing this series. So we're just doing this series here. 1 over n times n plus 1. Except I'm using this telescoping series part to realize that, hey, look, that cancels with that, that cancels with that, that cancels with n, on and forever. Okay. So then for any given partial sum, our S sub capital N is going to look like 1 minus, because everything else canceled, it'll be whatever this extra little term here is, which will evaluate to 1 over, it'll be the second part of whatever term this is, 1 over n plus 1. Okay. And of course, this goes to 1 as capital N goes to infinity. And since the series converges to 1, then its entire sum value, its entire infinite series value is 1, which is cool. But that's a telescoping series. The big thing about telescoping series, and it's called that, is because like a telescope, a handheld telescope, that you can retract it in on itself and make it much more compact. That's the idea there. Okay. Now, we can look at 31 here to determine whether or not this telescopes. It doesn't ask you to diverge or converge. It doesn't ask that. It just asks, does it telescope? Well, yeah, it does. How do we know this? Because we know that the natural log of something over something else, a over b, is exactly the natural log of a minus the natural log of b. Well, then the natural log of n plus 1 over n is equal to the natural log of n plus 1 minus the natural log of n. So if you do this series, it's going to collapse. It will telescope just fine. If you don't believe me, write the thing out. You will get something that looks like, you'll get the series natural log of n plus 1 over n to be, well, this is going from n equals 1 to infinity, so this will be the natural log of 2 minus the natural log of 1 plus, okay, and then the natural log of 3 minus the natural log of 2 plus the natural log of 4 minus the natural log of 3, so on and so forth, right? And then look at what happens here. Positive natural log of 2, negative natural log of 2. Positive natural log of 3, negative natural log of 3. That will continue so and so on forever. And it does, in fact, telescope. That's all that the question asked. Now, if you keep going, you can get that the nth partial sum is just the natural log of capital N plus 1 minus the natural log of 1, which is, of course, is 0. So that's just the natural log of capital N plus 1, and that goes to infinity. Therefore, capital N goes to infinity, the natural log of N plus 1 goes to infinity. Therefore, the whole thing diverges, even though it telescopes. So they don't always, telescoping series don't always converge, but it does telescope. Everything cancels infinitely. That's the whole point. That's all that we were looking for, which is why I didn't write out the rest of it. All right? Now, let's go on to the next section. In every single class you've ever been in, where you've learned math, every single math class, you have learned the definition of something, You have used the definition for a little while, and then you have discovered, oh, actually, there's a much better way to do things. Such is life, and such is the way that it happens in this class as well. Now, we just looked at the definition. Okay? The definition says that the limit of the sequence of the partial sums has to converge in order for the series to converge. And now, what we're going to do is look at a bunch of other ways that that we can figure out whether a series diverges or converges. The big idea behind all of this is this thing here called the test for divergence, or the nth term divergence test, if you will. The test for divergence says, if the limit of the terms of your sequence isn't 0, or it doesn't exist, then the series diverges. That is, remember, we're not looking at the partial sums for this. We're literally just looking straight at the sequence. And that's the beauty of it. We can look straight at the sequence. If that sequence is not going to 0, then the series is going to diverge, because you're always going to be adding finitely large pieces that are not themselves getting smaller and smaller. So, that's the central idea of the divergence test, is the actual terms of the sequence itself have to be going to 0 for convergence to be possible. Now, the most important thing about this is, notice it does not say that if the limit as n goes to infinity of the sequence equals 0, then it converges. It does not say that. At no point does it say that the limit as n goes to infinity of a sub n equals 0 means that the series itself converges. That is not true. But you can guarantee that if they don't go to 0, then it will diverge. So this is not a convergence test, it's a divergence test, and it only talks about divergence. Let me show you. This guy right here, let's look at the limit of these terms. Now remember, we start at 1, so this will be 1 over 3, right? So it'll be 1 over 3. The sequence is going to look like 1/3, okay? And then 2/4, right? 3/5, and so on, okay? So my question is, are these terms going to 0? Well, clearly not. Clearly, they're not going to 0. They're clearly going to 1, in fact. That is, we can take the limit as n goes to infinity of n over n plus 2, okay, which is the limit as n goes to infinity of, divide everything by n, top and bottom, and we get 1 over 1 plus 2 over n. This term goes away, and this whole thing goes to 1 in the limit, which you may notice 1 is not 0. So we can say therefore, that's what these 3 dots like that mean. That means therefore divergent. Divergent. So this series, we say the series diverges, okay? And when we say this, it's important that you tell me how you know that. How do you know it diverges? You can't just write that the series diverges and move on. Even with this chicken scratch on here, I would have some idea of what you meant, but the best way to answer this thing is by saying that the series, and you should write the whole series out. You don't have to write the n equals 1 to infinity part, but you should write the whole series out. N over n plus 2. You say that the series diverges, okay, diverges, and this is just called the divergence test. Diverges by, or the test for divergence, by the divergence test. So that's your answer, okay? And then the scratch work around here, specifically this part over here, is the rest of what I would be looking for. Specifically, the limit is something that isn't 0, therefore it diverges. That is you doing the test, and then this right here tells me that you understand what's going on. Those two things together would be the answer to the thing, okay? Let's look at this guy here. So what does this tell you here? Okay. Remember, we're looking at these terms. 1 over 1, 1 over 2, 1 over 3, 1 over 4. Okay. So on and so forth. Okay. The limit as n goes to infinity of 1 over n, we know that to be 0. Okay. Since we know it to be 0, the divergence test tells us nothing. Nothing at all. Remember, the test for divergence only works if a sub n, if this limit is not 0. Notice how this definition here tells us exactly nothing when it does equal 0. So, what does the test tell me? Well, it tells me that this equals 0. The test tells me nothing. Okay? That's the answer. The test tells me nothing. That's what the question asks. What does the test tell you? Now, if the question was determine whether this diverges or converges, what would you say? What would you say? Would you say that it diverges or it converges? You would say the series 1 over n is the harmonic series, because you've already written that down. Series, and you would say, therefore, it diverges. That's what you would say, because it is the harmonic series, and it does diverge. It's just a standard series. It's just something that you know. Okay? Let's do another one of these, and we've already done this one before. This was the one where I divided this square into pieces. But look here. Look at this piece. What conclusion can you make from the divergence test on this guy? Remember, this is 1 over, we start with 1 over 1 squared, so 1 over 1, okay? 1 over 2 squared, 1 over 3 squared, 1 over 4 squared, and so on. What can you say? What is this limit? Well, this limit's 0. Obviously, this limit is 0. Since the limit is 0, what conclusion can we make from the divergence test? Nothing. We cannot make a conclusion from this. Okay? There is no conclusion that we can make from this because it equals 0. There are many, many other tests. The integral test is right down here. I'm going to show you that one in a second. This is the first one that we learned. But there's many other tests that we can go on to. But this is the first thing that we've got to try. Just like when you're doing integration, you really want it to be an antiderivative or a u substitution. But if it isn't, we move on to other things. It is the exact same thing here. All right? So the divergence test only works if you get not equal to 0. So let me give you an example really quickly. Let me just erase all of this stuff. Let me give you an example in this box of one that you would actually be able to use it on. And it's going to be any time that you have something like this. Okay? So if you want this series, I want to know if this series, so from n equals 1 to infinity, does this converge or diverge? So we look at the divergence test on this. Okay? Look at the divergence test on this guy, and you'll see the limit as n goes to infinity of n squared over n plus 1. Okay? Now this is very clearly not 1. We know that, because we can essentially ignore everything in the denominator that isn't its highest degree, and everything in the numerator that isn't, and then we get n off of that. That's the way that I think of it, but you can do the math all the way out that's actually legitimate mathematics instead of that hand-wavy infinity stuff that I do. Divide both top and bottom, everything, divide it by the highest degree term in either. So the highest degree term is n squared, divide everything by n squared. So n squared divided by n squared is 1 on top. N squared over n divided by n squared is 1 over n. And then plus 1 over n squared. Okay. And you can look at that pretty clearly. And honestly, dividing just through by n would have been enough to deal with this, because this is going to end up giving us some really weird 0 plus 0 thing on the bottom. But you can see that this is going to, I mean, even this limit, this limit does not exist the way that we're doing it, but that's fine because it's not strictly 0. But you can also just divide through everything by n, which may be a little bit more helpful. So you'll get n over 1 plus 1 over n, which is a little bit easier to look at. And so this is going to give us an infinity over 1 plus 0. So this will go to infinity, which is just as valid. The particular point is that this limit It doesn't really matter what it goes to, whether it exists or whether it doesn't. It's not 0 is the point. And since it's not 0 by the divergence test, then the series diverges. That's the only conclusion it can ever come to by div test. So remember, it only matters, do you get not equal 0? Because if you get not equal 0, if you take the summand and you take the limit as n goes to infinity and you get literally anything but 0, then the whole series diverges and you're done. It's the first thing you should always look at. Unfortunately, it almost always is 0, and you'll have to go on to something else. All right? So let's look at the integral test real quick. So let's look at the integral test. Yeah. So let a sub n be some function of n where f is, okay, this is all very positive. This is all very important. It's positive, that is, at no point is a term ever negative. It's continuous, that is, there's no weird breaks in it, okay? And it's monotonically decreasing between 1 and infinity, including 1, okay? Then, both the series and its improper integral either both converge or both diverge. So something to keep in mind, if you've never seen it before, is this guy right here is called an improper integral. Because because either one or both of its bounds are positive or negative infinity, in this case its upper bound is positive infinity, or it integrates over some kind of discontinuity in the graph that isn't easily removable. Okay, those are all your different kinds of integrals. But what this actually means is this is the limit as b is usually the thing up top. So this is the limit as b goes to infinity of the integral from 1 to b of f of x dx. Just in case you've never seen this before. Okay, and if this evaluates to a number, then the integral converges. If you can't get it to do that, then it diverges. What the integral test says, and we don't do many of these, but what the integral test says is if you can get this integral to converge, then this series will converge. And if you get the integral to diverge, then the series diverges. So it's useful sometimes. Okay. Specifically, the function has to be positive, always. It has to be continuous. That is, it can't have any weird stuff going on. It can't have any weird holes in the graph. And it has to be decreasing from every number from 1, including 1, up to infinity. So we can look through a few of these. I don't usually put these on a test, but we can look at a few of these. And I guess it would be fair game since I'm teaching it. So the first thing that we need to do in any of these is determine whether or not this satisfies conditions of the integral test. Okay, so we're just going to give you an example, and we actually start with 2 here because natural log of 1 would obviously be a problem. That's fine. Remember, we're going to infinity here, so this number here is really just some number that makes sense up to infinity. That's fine. That's not a big deal. But the thing needs to be positive, continuous, and decreasing. Okay? So first off, we know that our function, f of x, okay, we know that it is greater than 0. That is, it's positive. We know that it's positive. So we're checked off on that. We know that it's positive. How do we know that it's positive? Because the numbers that we're plugging in start at 2 and go to positive infinity. So if you plug in a positive number here, and you plug in a positive number here, then a positive number times a positive number is going to give you a positive number in the denominator, and positive 1 divided by a positive number is a positive number. The whole thing's positive. We're good to go. Okay. We also know that it is continuous. X natural log of x is not 0 anywhere on here. The only way that this function can be discontinuous is if the denominator is ever 0. But we know that x times the natural log of x is always going to give us a number out, right? That is, it's never going to give us 0 on our interval from positive 2 to infinity. There's no number that we can plug in between positive 2 and infinity such that that number times the log of that number gives us 0. We just won't be able to do it. That's why we didn't start at 1, by the way. So we're good to go on there. And then We need to know whether it is decreasing, because now we know it's continuous. Now we need to know whether or not it is decreasing. So is it decreasing? Well, we know that x, as x gets bigger, x gets bigger. We know as natural log of x times x gets bigger, then this whole thing, this thing increases, right? This thing increases, INC period. This thing increases as x gets big, okay? That means that it's reciprocal 1 over that. That means we're going to be dividing by a larger and larger number. So this thing is going to go to, well, 0, right? That is therefore it decreases as x goes to infinity. Okay, so it is decreasing also. So it satisfies the conditions of the integral test. So that's cool. So then you could determine whether or not this worked with the integral test. You're welcome to use the integral test now. That is, you're going to take the integral over your bounds from 2 to infinity of 1 over x, natural log of x, dx, and go off and do your thing and figure out whether or not that gives you a number or not. If it gives you a number, then it is convergent. If it doesn't, it doesn't. But we're not going to do that one because all that this thing said, remember, read the instructions, it just says, does it satisfy the conditions of the integral test? Which is a perfectly fine question for me to ask. I don't want to do that integral because I can't do that integral in that small amount of space. But I can do this integral in this small amount of space. So let's do that. So, determine whether or not this function satisfies the conditions of the integral test. That's all that we're going to do again. So we're not going to determine whether or not it converges or diverges. Does it satisfy the conditions of the integral test? Pause. Rewind the video a little bit after having written this down and see whether or not it works. But the 3 things that we need to know are, is it positive for everything greater than 1? So think about plugging numbers in here. Is 1 divided by, well, it doesn't matter what number we plug in. When we square it, it'll be positive. So f of x is always positive, right? So we know that it's always, so that is, we know that f of x is always positive. That's true. We know that. Check. That's step 1. Okay. Step 2 is going to be, is it continuous? Is 1 over x squared continuous? Right? Is 1 over x squared, is it continuous on this integral, on this interval from 1 to infinity like this? Is it continuous? Is there any number that we can plug in that's going to make the denominator of this rational function 0? No. The only 2 numbers that we can plug in to the denominator to make it 0 are 0 and 0. Because that's what the roots of x squared equals 0 are. 0 multiplicity 2. Well, 0, you make notice, isn't in here. So we're good to go on that one. And the last one is going to be, as x increases, notice that x squared decreases. Or rather, as x increases, x squared increases. So its reciprocal decreases. So then 1 over x squared is decreasing. It's decreasing on our interval from 1 to infinity. So then, yes, it meets all 3 of the pieces that we need. So let's scroll on down here and let's look at whether this thing converges or diverges using the integral test. Okay, now we're finally going to do this, all right? So, we've already done this problem and we know that it meets the conditions. So we're welcome to use this. So we did this back in 35. We know that this works. So, I'm now going to take the integral from 2 to infinity, okay, of 1 over, change the variable to x so that it's real, x log x dx instead of discrete in n. Okay. So a standard antiderivative for this, if you go do all of the math on this, this is one that you would look up in a table at the back of your book, by the way. It's the natural log of the absolute value of the natural log of x. Believe me, getting to that is a pain, and that's hardly the point of this, plus c. Okay. So then we say that the integral from 2 to infinity, okay, of 1 over x natural log of x dx. Okay. This is, forget the bounds on this for a second, just so that you can see that up here. So then this is going to be the limit as b approaches infinity of the integral from 2 to b of 1 over x natural log of x dx, which is the limit as b approaches infinity of the natural log of the absolute value of the natural log of x, which you don't have to put the absolute value anymore since these are always positive numbers anyway. And then, of course, we're going to evaluate that between 2 and b. And then you'll see that this is the limit as b approaches infinity of the natural log of the natural log of b minus the natural log of the natural log of 2, right? Which is going to be, which goes to infinity, right? Because as b gets infinitely big, this guy gets infinitely big. And this is just a very small number. So a infinitely large number, this goes to infinity as b does. Very slowly, insanely slowly. But it does go to infinity. So then this whole thing goes to infinity. Then the integral converges. So therefore, both the integral and series diverge. Because this integral diverges. We say that this integral from 2 to infinity, we say that this diverges. It diverges because it doesn't equal some number. And so that's an example of the integral test. Okay? Now, I'm going to do one more of these. I'm going to actually leave the next one for you for some practice. Because truth be, I have many, many, many more of these. And I don't really want to belabor the point on this. So let's do this one right here. This is easy enough to just work through. So we need to look at whether this needs to be positive, continuous, and decreasing. But we know that because we've already done this one. We did this one back in 36. So it meets the criteria to work. Okay. And that's the first thing. It needs to meet the criteria. So now we're going to look at the integral from 1 to infinity of 1 over x squared dx. So we know that the integral of 1 over x squared is negative 1 over x plus c, because this is the integral from 1 to infinity of x to the negative 2 dx. So when you do the math on this, this ends up being, and this is sort of sloppy to write it this way, but this is negative 1 over this is negative 1 over x evaluated between 1 and infinity. So then this is, you can think of that like negative 1 over infinity, which is 0, minus negative 1, which is 1. So then this whole thing is going to converge. Then 1 over, therefore, we can say therefore, the series converges by the integral test. Of course, doing the integral test on this is not a great idea. I only did it because it said to. This is a geometric series. It converges because it's a geometric series with r equal to a proper fraction. But this is a way to do this. Now, you're welcome to pause the video and give this one a shot if you want, by all means. I'll go ahead and tell you that you end up getting that this one diverges, This one will diverge because you end up at the end of this with the limit as b approaches infinity. That's an approaches. So b approaches infinity of 2 square root of b minus 2, which is clearly infinity. Therefore, the whole thing will diverge. You'll end up with that at the end if you want to do all the work on that. And then this guy is actually called a p-series, and it's got a completely different sort of definition. But when you get to the end of this, it ends up showing how this works. But the point of this guy is actually kind of cool. I wanted to prove this, but I don't think that it's actually worth the time. This guy's called a p-series. And we're going to write down a couple of things, okay? So the series, it converges, okay? So it converges, okay? And then when it diverges, okay? So it will converge, okay, when p is greater than 1, and it will diverge when p is less than or equal to 1. So that's true. So anytime that you see a series like this, it will converge when p is greater than 1, and it will diverge when p is less than or equal to 1. That's it. That's called a p-series. That's the only thing that is. That's another type of series, just like the geometric series, that you should write down and know. You're hoping that you see something like n equals 1 to infinity of 1 over n cubed. Okay? Because that guy is going to converge because this is bigger than 1. But if you see the series n equals 1 to infinity of, say, 1 over n to the 1/3, that will diverge. Okay? Because 1/3 is less than or equal to 1. That's it. That's the p-series, and it's a whole class of them, and it's really easy to do. Proving this fact is doing this problem. So you determine, you can do the integral test on it, and then you break it into cases. If p isn't 1, you'll do it, and then you'll do another one where p equals 1, and then it will depend, the integral will depend on the integral, and you can look at it that way. And that's the way that you end up doing that. It's a cool little proof. It's actually done in your book if you want to look in your book. You can also look up proofs of the p-series online, and you could find people spending hours going over this. But I just wanted to show you an example of this, and this was how I reminded myself that this is when this usually shows up in class. Now, there's actually some pretty cool stuff on this that you can do with something called the remainder estimate. It's called an integral test. It comes from the integral test. And it's the idea of approximating error, of approximating a series by using a partial sum. And so you can stop after a certain point and find an amount. But remember, if the whole series converges to some number, how close are you? Is the idea that this thing ends up looking at. Right? And then you can get the remainder out of this thing. And so the remainder is always going to be the integral from whatever number of terms you want onward. So in this case, and I just want to show you this so that you've seen it, because it is a core competency of the class. But it isn't something really important, and I promise this won't be on the test. But you're doing something like this, and it'll have to satisfy that in particular. So when you compute that, and you go through and you do all that math, you'll get that this, because when you do the math on this is a fifth. So then we're within a fifth. The remainder after 5 terms will be within a fifth of the term, is how this is going to end up working. You've now seen this, and we're going to move on to the next section, in fact. Let's talk about the direct comparison test. As opposed to the limit comparison test, which we're going to do in a second, it requires a couple of things. One, it requires that all of your terms be positive. And it also requires 2 different sequences. So this is difficult to use because you have to pick the other sequence to compare it to. It's the hardest part of the comparison test, but it works like this. Both of them have to be positive. That's what this says. And there is a test, there's a sequence that is bigger than another sequence here. Now, this actually says for all n. That doesn't actually have to be true. This is stronger than it has to be. It actually has to be for all you pick some n greater than or equal to n. That is eventually. At some point this is true, and then it's true forevermore. So at some point you've got two sequences, and the terms in this sequence, the second one, are bigger than the terms in the first one. And you, at some point in the sequence, it's true, and then it's true beyond then. For all n is a stronger requirement than you need, but it's also true. But this is actually more true. So this is actually what the OpenStax book says. This is what some other books require, and I must have pulled this from another book, but that's what this is. But it says this: if the series involving the bigger sequence converges, then the smaller sequence, then the series involving the smaller sequence also converges. The other one says that if the series involving the bigger sequence, the smaller sequence diverges, then the bigger one diverges. And let me show you the idea on that. So pause it and write this for all n greater than big N down. That's the eventually part. And you really can just say eventually. That's what that means. It doesn't have to be for all n. But it works like this. Think about this. You've got some 0 here. I'm going to talk about this first one first. Okay. You've got some term here. Okay. And you've got it such that at some point, all of your an terms, which will be in blue, are doing something. As a matter of fact, let me just go back a little bit and do it a little bit more like this. They're doing something like this. Okay. And they can be hopping around and doing whatever. Okay. But you've got your bn terms, and remember it's bigger, so it's higher up, and it's doing this. It's converging towards the blue line, and it's eventually going to be at the blue line, like that, right? What it's saying is this is your b sub n, okay, and this is your a sub n, okay, and you're headed towards your L down here, your convergence down here. What it's saying is that since an is hemmed in by whatever your limit is, and b sub n, at some point, this has no choice but to go where it goes. That's what it's saying. So the strategy with this is going to be, in both of these, you're given this one. This is the one that you're given on the piece of paper. You get to choose this one. You get to completely make it up. So for this one, you'll choose one that converges. For this one, you'll choose one that diverges, because for this one up here, you're trying to prove convergence. For this one up here, you're trying to prove divergence. By the way, it's the same sort of logic for this one, for the other one here, and I'll show you on this one. So here. This time, you're going down towards here, okay? And if your a sub n is wildly out of control and is clearly not headed anywhere towards that line, then your b sub n, no matter what it's doing, it can never get below that, so it must never be able to touch the line. That's what the second thing says. Even though I reversed the colors on accident. Sorry about that. But that's what that means. So that's what we're working with. So we can use a direct comparison test to talk about here in our life, universe, and everything example, whether or not this is going to converge or not. So do we think it converges, or do we think it diverges? And this is where knowing what geometric series and p-series look like that's going to be really helpful. So we can figure out whether this thing converges or diverges. So this right here is our an. It's always an, by the way. In all of these definitions, that's our a sub n. So we have our a sub n, and we have to guess, just based on intuition, whether we think this is going to converge or diverge. So the first thing that we want to use is, first off, it says to use direct comparison, so that's what we have to do. But if it just said determine whether it converges or diverges, which is the only problem I'm ever going to give you, although I guess I might say specifically if I want you to see this. I guess I could. But the one that I like to give you is just determine whether it converges or diverges. What we would try first is, well, let's try the limit test first. Is the limit as n goes to infinity of this thing anything other than 0? Because in that case, it diverges. That's the test for divergence. Well, that's not the case, right? That's not the case. This clearly goes to 0, so crap, we're out of luck with that. Okay, then let's actually try direct comparison. So I'm going to guess that this converges. So I'm going to choose my BN, and so I'm choosing converges up here. I'm choosing converges. So then I need this to be the relationship. I need to be this to be the relationship. So if this is going to be, then I need to set it up such that it's like this. That is, I need to choose my BN so that it hems it in. I need to choose a convergent series. Well, I know this converges. This is a P series with P equal 2. That will converge. So now all I need to do is convince myself that this is true. Is this true? Well, they're both certainly always positive, so this part's true. How about this part? Is 1 over a slightly larger number than this always going to be less than? Of course. Because n squared plus 1 is greater than or equal to n squared, then their reciprocals, you flip the sign. That's how that works. So that's true as well. So then by what we call the direct comparison test, or just the comparison test, by direct comparison test, by direct comp test, right, we can say series converges. And this, together with this bit, is what your answer would be. Okay? Now, the hardest part of this, and you really do need to write down that definition so you can look at it when we continue through the video. The hardest part of this is understanding when to use which of those. Because, brother, that can get difficult. You have to have some semblance of an idea as to whether or not the thing converges or diverges. So let's look at this one. Let's use a direct comparison to determine whether or not this diverges or converges. Now, it is going to diverge, but the question is always going to be that you're going to be given is it converge or diverge? You don't know. You don't know. But you do know that if you just get rid of this plus 1, brother, that's a P series again. That is the P series. If you just can get rid of that plus 1 in your head mentally for a second, because remember, you get to choose what you compare it to. This guy right here, remember, square root of n is just n to the 1/2. This is a P series with P less than 1. P less than or equal to 1, right? So this is going to diverge. So if I if I can just get rid of that little plus 1, then I can compare against that. Well, then let's compare against that, and let's compare the divergence part. That is 0 less than or equal to, the divergence part puts our a sub n on the outside so that it's forced away. Go back and watch that part of the video again, and then I'm going to pick this guy. Or, if you prefer, this guy. Now the only question is this true? Is this always true? Is 1 over the square root of n always going to be less than or equal to 1 over the square root of n plus 1? It worked in the last one. Is this always true? Think about it. It is not. The reciprocal's true. N to the 1/2 less than or equal to n to the 1/2 plus 1. That's true. But then if you do the reciprocal, you'd have to flip this sign. So you cannot compare directly against this. Be very careful and make sure that that works out. They're both certainly positive, so that works. But this is not true. So you cannot make that comparison. You would miss this problem if you did that. However, there's a really quick fix on this one. You can just, remember, you get to choose any series you want. You can just put a 2 there. And now that's definitely true. Now that's definitely true. And you didn't really mess anything up. Remember, multiplication's always more powerful than addition. So that's definitely going to be true. And we still know that this diverges. right? Because it's a p-series with n equals 1/2. Because remember, the series 1 over 2 square root of n is equal to 1/2 times the series 1 over the square root of n. And since we know that this diverges because it's a p-series, then the whole thing must diverge. Since this diverges, remember that graph that we drew, right? We've got this guy here, and in blue, that's the guy that we're doing. It's going to diverge eventually, so it's not going towards the line. And so it doesn't matter what 1 over square root of n plus 1 does. It's always less than it eventually, so it has to diverge also. That's the kind of picture that we're looking at. So then this thing will diverge. So the entire answer is series 1 over square root of n plus 1 diverges, div is fine, by the direct comparison test. Direct comparison test. Okay, and if you want to be super exact, you'll say with, so w slash with, you can write out with, 1 over 2 square root of n, if you want. That's fine. All of the work on the paper is enough to show me what you need. But this sheet of paper, this thing right here, tells me everything that I need. It tells me does it converge or diverge, it tells me why, and it tells me what you did. That's actually enough writing. However, writing all this stuff out and the scratch work is going to be how you get the majority of the points on this, all right? So, this one here says determine a useful comparison for this guy. So you don't have to do it, you just have to determine a useful comparison. How do you determine a useful comparison? Do you think this thing's going to converge or diverge? Well, take the limit as n goes to infinity of the summand, you get 0. So we don't know anything because it isn't something other than 0. Right? If we got something other than 0, then it diverges and we don't have to worry about this. But it is 0, so yeah, let's determine a useful comparison for it. And, well, if we factor the denominator, we get n squared plus n equals n times n plus 1. And so we might think that when n is getting really, really super stupid big, that the dominant behavior as n goes to infinity, this n squared term is going to be much bigger. So maybe 1 over n squared might be what we want to compare it against. So we ask the question, well, do we know anything about 1 over n squared? Does this converge or diverge? It converges. Why does it converge? Because it's a p-series with p bigger than 1. It's 2. This is going to converge. So since it's going to converge, then the setup is this. The thing that we're investigating needs to be hemmed in. Those pictures are actually how I remember this. So then the question is this true? Then we can go ahead and finish it off. Well, of course that's true. This is all going to be positive. And then the question, that's not always true, by the way. Always check it. Are all the terms always going to be positive? Eventually, at least. And then over here, is this true? Well, obviously adding a number to the denominator is going to make the denominator bigger, which is going to make the whole thing smaller, which, yeah, that's going to work. That's going to work just fine. So then that comparison is going to work. Okay? So, here's just some general stuff, and then we're going to do this. Try to compare them to simpler terms. Okay? Compare them to 1 over n over p. That is a p-series. Compare them to the geometric series that we've already studied. And then compare them to the dominant terms in the numerator and denominator. Okay? The dominant terms in the numerator and the denominator terms of this guy are, look at this, 3n plus 1 over n cubed plus 1. The dominant terms are, the biggest degree term is 3n to the 1 in the top, n cubed in the bottom, right? So this goes to 3 over n squared. So then what we're going to compare to is just 1 over n squared. That's going to be enough. That's fine. We know that this converges. So then we're going to set this up like it's a convergence. Okay? And that's how we're going to continue with this. How does the convergence work? The convergence works, remember, it's always 0 less than or equal to one of the terms less than or equal to another one of the terms. Okay? your term that you pick is what's important, okay? So if you're putting your term that you pick here, you're saying that the original thing goes here and that it converges because it's hemmed in. If you put your original thing here, the thing that you determined here, and you're putting the summand that you were given, this thing, if you're putting it here, then you're saying that it's going to basically run it out of the road, which I've shown you multiple times, which means that that's going to diverge. So where you put your choice matters, right? So this is about your choice, your choice. Because remember, you determined this guy. So, right, so if you put your choice here, if you put your choice here, then you're saying that the term diverges. If you put your choice here, then you're saying that it converges. You're not saying that your choice converges or diverges. You're saying that the original thing converges or diverges, right? Now, maybe another way to remember it is going to be, where do you put the original summand at? Where do you put the original summand at? Let's do that in a different color. Where do you put this guy at? Okay, the summand. Okay, where do you put the summand at? If you put the summand here, you're saying that it's going to converge. Because you put your choice here, and you know that it converges, therefore you're saying that it converges. If you put the summand out here, you're saying that the summand is going to diverge. And that's probably a better way to think about it. So it's wherever you put it. So convergent, divergent. It's wherever you want to put the summand at, but that's going to tell you what you're trying to do. So if you put the summand here, then you need to pick something to put here. Your choice needs to converge, right? If you put the summand here, then the thing that you put here needs to diverge because they need to match. Both the thing you pick and the summand that you're trying to evaluate need to both either converge or diverge. That's the most important part. I hope that makes some kind of sense. So let's choose a comparison test for this and determine convergence or divergence. The easiest way to look at this guy, okay, is look at the top and the bottom. 1 over root n, which remember is n to the 1/2 plus n, right? Which one of these two is bigger? Square root of n or n? N. So compare this to 1 over n. Does 1 over n converge or diverge? It diverges. Then set it up like this. You want divergence, so then the thing needs to get ran out of the road. The thing needs to get ran out of the road, so it needs to look like this, such that your thing is here, and such that it's like this. Okay? It'll always be greater than or equal to 0. These are obviously both always positive, right? Is this going to be true necessarily? Is 1 over root n plus n going to be greater than or equal to this? No, that is not true. That is not necessarily true. However, this is going to be true, so then we can use that instead. Because, keep in mind that the bottom of this over here, right? The bottom of this over here, root n plus n, is going to be less than or equal to just n plus n, which is 2n, which is what we want, right? So that'll be true at least. So that's nice. So make sure that it works, and if it doesn't work, honestly, you can usually just slap a 2 in front of the denominator and it'll work out just fine. Make sure that it does. And if it doesn't, then make the denominator bigger by putting a 12 in front of it or something. You can choose anything you want, just as long as you're trying to determine convergence correctly. We determined that this is probably going to diverge. We just need some form of the harmonic series. Well, it just needs to be multiplied by 1/2, apparently, and then we're good. Cool, that's it. Now, the next one of these is called the limit comparison test, and it is so much easier to work with. Okay? It says that as long as your sequences are positive, and by the way, it means that it's positive eventually, at some point, and then forevermore, your terms are positive. And if your limit, as n approaches infinity, of an over bn is some number bigger than 0, then both of them either converge or diverge. Okay. This is cool because you get to use a bunch of math in it. You're not strictly speaking choosing things and trying to put things in the right place. It's always an over bn. You're always going to make it look like this. But remember, a sub n is always going to be the thing that you're given. B sub n is always going to be the thing that you choose. So this will always be the thing that you're given. Okay? B sub n will always be the thing that you choose. In all of these, in every definition that I give you. A sub n that's the problem. B sub n is something that you're making up. And since they both have to converge or they both have to diverge, then you better know something about the thing that you're choosing. You better know whether it converges or not. Okay? Now, notice that in n over n squared plus 1, okay, that this is approximately equal to, and we'll just use a single tilde to represent that, this is approximately equal to 1 over n. How did I do that? The same way I've done it every single time. I look at the highest degree in both of these, okay, and I just divide all of this out. So when you reduce all of the powers down, you get 1 over n out of this. These are approximately the same sort of thing. So I'm going to compare against 1 over n. What do I know about 1 over n? That's the harmonic series. It diverges. How do I know it diverges? Because it's the harmonic series. How do I get from n over n squared plus 1 to know that 1 over n is what I need to compare with? Because this is n to the first and this is n squared. So then that is roughly equivalent to, that is basically, I get to ignore this. As n gets big, which is what happens, look here, as n gets big, that's what we're working with, this is approximately equal to n over n squared, which is, again, about 1 over n. I mean, this literally is 1 over n. That's what I'm saying. That's how I got there. So I'm going to compare it. So then let's compare it. Let's do the test. By the limit comparison test, we do the limit as n gets real big, okay, of our a sub n. That's the thing we were given. N over n squared plus 1. Divided by, big divided by, what we're comparing against. 1 over n, okay? This is the limit as n goes to infinity of, change flip, so keep the top, plus 1, change the middle division to a multiplication, and then multiply by n over 1. And then this is the limit as n goes to infinity of n squared over n squared plus 1, which is 1. We know that. Because again, as n gets infinitely big, we only care about the dominant terms on the top and bottom. That is the terms with the biggest exponents. So that plus 1 really doesn't matter. And n squared over n squared is 1. The limit as n goes to infinity of 1 is 1. Okay. What does that tell us? The limit is a positive finite number. It equals c, and it's positive, right? So we say that this is greater than 0. It's a positive finite number. Okay. So we know that. Then they're either both going to converge or they're both going to diverge. What did we compare against? We compared against something that diverges. So therefore, we say the series, okay, we say the series n over n squared plus 1, okay, diverges by the limit comparison test with, what are we comparing it against? We're comparing it with 1 over n. That's it. That's how you do that. It's the same strategies for picking your b sub n, except you can just chuck it into a limit and do the math. This is almost always a better thing to use than the comparison test. So unless it specifically says to use the direct comparison test, which is also just known as the comparison test, use this. The limit comparison test is always called the limit comparison test, and it's where you compare things in a limit as a test. That makes sense. Cool. Let's try this one. Let's go ahead and do log n over n. What are we going to look at with this? Well, we're going to compare it once again with the same thing. How do I know that? Look here. Natural log of n grows super slowly. That's kind of its whole thing, right? This grows super slow. This grows comparatively fast. So then this is roughly equivalent to 1 over n. That is, as n gets super big, this grows so slow that it may as well be a constant. This is an idea from Calculus 1, by the way. So we're going to compare it against the exact same thing. So we're going to do the limit as n goes to infinity, okay, of the thing that we're comparing against, log n over n, okay, over 1 over n. This equals the limit as n goes to infinity of, keep, change, flip. We're going to get log n over n times n over 1, and those n's are going to cancel. So this will just be the natural log of n, which goes to infinity. So, what is this? What happens here? Remember, the limit comparison test requires that the limit be a finite positive number c. So the question that we've got to ask ourselves is, on this guy, did we get a finite positive number c? No, we got infinity. So the LCT here, LCT does not help. Okay? And that's all that we can say. It doesn't give us a finite positive number. So we cannot say anything about this. Now, you could use a direct comparison test, right? You could notice that as long as n is bigger than or equal to 3, that is eventually, natural log of n is going to be greater than 1. So, natural log of n over n is going to be bigger than or equal to 1 over n. Therefore, the whole thing will diverge. That is, you're going to be able to set this up eventually. This. And since the thing that you're wanting to compare is on the outside, you're testing for divergence. And since this thing actually does diverge and these actually work out, then the whole thing will diverge. We'll say the series diverges by the direct comparison test. So here's an example where you might actually need the direct comparison test. So I would just give you the problem, determine whether the series log n over n converges or diverges. It's completely up to you. So you can try this test, but you don't get it. You can try the limit comparison test, but it doesn't reveal anything. Well, dang. But that's okay. That's not a big deal. You can just use a different test. That's all you have to do. Use a different test. By the way, the limit as n goes to infinity of this is 0, so the direct comparison test doesn't work. It basically never works, but sometimes it does, and that's cool. Anyway. Oh yeah, here's a p-series. And we've already talked about a p-series and how the integral test works. So you're welcome to write this down now. But we can go over those really quickly. But let's do one more with a limit comparison test to see what's happening. You're not going to believe this, but we're actually going to compare to the exact same thing again, the way that I wrote this out. And I don't really like this example. We're going to try a slightly different example. Let's just forget about this one. Let's do a different example, because this is going to diverge, and it's going to diverge against the same test. I don't want to do the same test again. So let's do this test. Let's do n equals 1 to infinity. Let's use limit comparison on this one. Let me just switch those numbers. So 2n cubed plus 3 over n squared plus 1. Let's try doing a limit comparison test against that. So when we look at this, right, when we look at this, we get 2n cubed. We look at just the dominant terms. Okay, we get 2n. So we could compare against the series 2n if you wanted. So if you compare against the series 2n for this, which is fine, that diverges for sure, because you're just going to add more and more bigger and bigger numbers forever, right? Like we're literally comparing against the series n equals 1 to infinity of 2n. That's add together all even numbers. Well, that clearly isn't going to be number. That's going to be infinity. But we can compare against it and show this. So the limit as n goes to infinity. Let's see if this even works since I just made it up. So we're going to put our term on top. So 2n cubed plus 3 over n squared plus 1. And then we're going to divide by just 2n. So we're going to, this is 2n over 1. We're just going to keep, change, flip. So that will give us, let's see here, to the limit, sorry, as n goes to infinity, of 2n cubed plus 3 over, let's see here, we'll distribute through the 2n's. So it'll give us 2n cubed plus 2n. Okay. And then we can look at the limit as n goes to infinity of that. That's going to be 1 because, remember, n's getting big. We only care about the dominant terms, right? So these are just going to go away. We only care about, in the limit. That's very important that we're getting big. You can't do this otherwise. But like everything cancels and you just get 1 left, right? So since this is 1 and it's bigger than 0, that is, it's a positive number, we can say something about this. And that means that this term, this series, and this series are either both going to converge or diverge. We know that this diverges, therefore this diverges as well. So we know that it diverges. So we say that series diverges by the limit comparison test with 2n. And that is your answer right there. All right. So define the p-series down here just to make sure that we get this. I never did formally define it up above. It just shows up in the integral test. But this is the p-series. It converges here. It diverges here. You've already written this. These are really quick. You're just looking at p. Is 3/2 less than or equal to 1? No. Is it greater than 1? Yes. Then this converges. 1 over n. That's n to the first. It's equal to 1. And look here. That's why we put the equal to on here. So this will diverge. Of course it does. It's the harmonic series. P-series test to test this guy here. So how do we do P-series with something that looks like that? That's a good one. So let's look at this before we move on to the next sort of thing. So we look at how does this behave for large n. So for large n, this guy, square root of n plus 1, is kind of like the square root of n. They're kind of like the same sort of thing. So then what we're actually dealing with is, for large n, we're actually dealing with the series. Remember, you don't have to write all the extra ornamentation on it if we're just determining some stuff. This kind of works like this, which is, of course, just 1 over n to the 3/2. And then you just look at this, and you determine that, of course, it converges. And that's it. You're welcome to compare that if you want. You can use the comparison test to reach the same sort of thing. But the p-series, you can just say that, for large n, for large n, that's true. Therefore, series, right? That's a sigma. It's a very bad sigma. Series converges by p-series. And that's fine. If you want to actually say that it's a direct comparison test, and you want to come in here and you want to set up the comparison test as n plus 1 less than or equal to 1 over n to the 3/2. And right, we know that converges, therefore this has to be squeezed into converging. These are both positive terms, and this actually is a true statement here. You're welcome to do that and then say that the series converges by direct comparison test with 1 over n to the 3/2. You're welcome to say that. That's technically more correct, but this is so close to just being a p-series that honestly, if you just use this little magic word here, that's going to be super useful and get you pretty far. So let's move on and talk about alternating series. So an alternating series has terms that, you're not going to believe this, guys, alternate in sign, okay? Typically, it's written like one of these two ways, and it's just, does the alternator have a plus 1 on it or not? It doesn't matter. The real thing is that your sequence is greater than 0. Your terms are all positive. And that's very important. Your terms all have to be positive. So first off, let's just make sure that we understand how to write this out. So the first 5 terms of this are going to be your a sub. Remember, we start here. We start with a sub 1. A sub 1, a sub 2, a sub 3, a sub 4, and a sub 5. Okay, like that. Equals, 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 equals. Okay, cool. So this is going to be negative 1 to the 1 plus 1, 1 over 1. Negative 1 to the 2 plus 1. So 1 over 2. Negative 1 to the 4th. This will be a negative 1 to the 5th. This will be a negative 1 to the 6th. And this will be 1 over 3, 1 over 4, and 1 over 5. And that's just multiplied. Well, that's positive, so this will be a positive 1, a negative half, a positive third, a negative quarter, and then a positive fifth, and so on and so forth. That's what the first 5 terms of that look like. And notice that they alternate in sign. That's the big thing. That guy's positive, negative, positive, negative, positive. That's why it's called an alternating series, because the terms alternate in sign. That's all it is. It's a series with an alternator in it. Cool. So write out the first 4 terms of that guy right there. Let me just write out the sum. That is, you're literally just doing the sum from n equals 1 to 4 of negative 1 to the n 2 over n squared. We can do that. Sure, why not? That'll be negative 1. So all the n's in this term are going to be 1. So 1 over 2 over 1 squared plus, okay, the next term will be a 2. So the next term will be a, whoops, the next term will be a 2 here. 2 over 2 squared, okay. Plus, and I'm going to show you how to wrap these things around. I guess that'll be a useful thing that'll be taught in here. Negative 1 cubed, 2 over 3 squared, okay. And then when you write a plus, okay, anytime that you write a plus, the plus, if you're going to word break like this, do not write the plus up here and then write a term down here. Don't do that. Write the plus with the actual term itself. So plus, not the series, love. Wow. Plus, Lord, wow. Plus, negative 1, I've been talking for a little while, y'all. Negative 1 to the 4th, 2 over 4 squared. That's what the first 4 terms of that would be. Now, let's talk about the alternating series test. This series converges if, first off, this guy needs to be decreasing. And then the limit of that term, that is, without the alternator, is 0. That's it. Is it decreasing? And is the limit of the term 0? Now look here. Remember, the test for divergence cares about this, right? But this is for an alternating series test. So if you throw an alternator in front of it, if an alternator is in front of it, then the alternating series test only cares if, is this decreasing, and are the terms getting small as you move on? Infinitely small, towards close to 0. Because of course, if, again, that's 0, right? That's 0. Here's your terms an. If it's decreasing and you're getting there, absent your alternator, it doesn't matter whether it's both. If this is what the terms are doing in their absolute value, clearly it's going to converge. So let's just take a look at that really quick. Okay. So this is example 55. Let's take an example of it. Let's look at this really quick. So this is an alternating series, and that right there is a sub n. Okay, that right there is your a sub n. The way that this is written, and so actually in your text, this is written as b sub n. This is written as b sub n. Because a sub n should technically be this whole thing, right? But it's really, for the alternating series test, you're testing the part without the alternator on it, right? So what we're going to do is, first off, is 1 over n decreasing as n gets big? Is it 1/2, 1/3? So 1/2, 1/3, 1/4, 1/5, so on and so forth. Is that decreasing? Are the numbers getting smaller? Yep. Okay, and then let's look at the limit as n goes to infinity of, and this is the important part, everything except for the alternator. So take the alternator off, look at everything else. What is this? Well, this is very clearly 0. Well, then this converges. AN is decreasing, the limit's 0. So we say by the alternating series test, series with the alternator in it, -1 to the n plus 1, 1 over n, converges. So that plus the scratch work on the paper is going to tell me everything that I need to do. You have to check to see if it's decreasing and if the limit equals 0, at which point you're fine. Okay? Let's look at this one. Let's test to see if it converges. So remember, you look at just this. So first off, 1 over the square root of n. Okay? How do you know if it's decreasing? Like, how do you write that mathematically? That means that each term, right, each term is bigger than, strictly bigger than actually, strictly bigger than its successor, the next term. Well, the term after n is n plus 1. So is that true? Of course that's true. Of course that's true. So 1 over n is decreasing. 1 over root n is decreasing. Then we look at the limit as n goes to infinity of 1 over root n. You're never going to believe it. That's also 0. The top stays fixed. The bottom gets infinitely large. 1 over a really big number is the smallest number there is, 0. So since both of those are true, we say series -1 to the n, 1 over root n, converges by the AST, by the alternating series test. This one's really easy to use. You check a couple things and you see if it works. Okay? But remember, the conclusion that you're making is the series involving the alternator. But what you're testing is everything but the alternator. That is, you're testing at an absolute value. You actually say that it converges absolutely, but we'll move on. Okay? Let's test this guy for convergence. You're never going to believe how we do this. We check to see, first off, is it true that each term is strictly bigger than, add 1 to both of the terms, n plus 1 over n plus 2. Is that going to be true? Is that going to be true for all n? Yes, of course that's going to be true. So n over n plus 1 is, in fact, decreasing. You can tell that it's decreasing by looking at your notes there. Okay. So then the next thing is we look at the limit. We look at the limit as n goes to infinity of n over n plus 1. Well, as for big N, we don't care about that. Those go away. That's essentially 1 over 1, so the limit is 1. So 1, you might notice, isn't 0, which is what we need. So what do we tell? What do we say? Let's zoom back up. What does it say? It says the series converges if these things are met. So by the alternating series test, we can't conclude anything because this doesn't equal 0. Okay? However, this is one of those cases where the straight up test for divergence will tell you that this diverges. We know that this diverges because the limit as n goes to infinity of -1 to the n over n plus 1 does not equal 0. So finally, what is called in the notes the nth term test for divergence, it actually isn't 0 for once. So then we can say, therefore, the series diverges by the divergence test, which we learned way back in example 20 or something like that. Divergence test. That's enough. Cool. My brain's starting to fail. Let's keep going. So, if you want to check conditions, first off, show that a n plus 1 is less than or equal to a sub n. The way that I was writing it, by the way, was a sub n is greater than or equal to a sub n plus 1. We usually want to check to see, by the way, that it's strictly greater than most of the time, but equal to can work. But obviously, if they're all the same term, you're going to run into some issues. 1, 1, 1, 1, 1, 1, 1, 1, 1, 1 is technically, by the definition, the sequence of all ones is technically decreasing. Technically, by that definition, I don't like that definition so much. But then you also have to show that a sub n equals 0. So if you want to just verify the conditions of this really quick, remember, you just look at this and you ask, first off, is that going to be decreasing? Yeah. As you plug in bigger and bigger n's, the bottom is getting bigger faster than the top is, therefore the whole thing's going to be decreasing. So for this example, you'd be fine. And then you have to show that the limit equals 0 for this. Can you show that the limit equals 0 for that? Well, yeah, you sure can. Now, you've got to look at this a little bit differently. This is one where you've actually got to use L'Hopital's rule to figure it out. But you want to show that the limit equals 0. Well, let's remember L'Hopital's rule. So I'm actually going to look at it in x, because I want to look at it in x. Because I know I'm going to have to take a derivative eventually. But you can look at it in n and take the derivatives in n. That's fine. But I'm going to look at it in x. I just change the variable to be something real. If you plug in infinity, you get infinity over infinity. Okay? So I'm going to use L'Hopital's rule. And that says I got to take the limit of the top and the limit of the bottom. The derivative of the top and the derivative of the bottom. Okay? So I'm going to do that. What is the derivative of the top? What is the derivative of the top? The derivative of the natural log of x is 1 over x. What's the derivative of x? 1. Okay, so this goes to 0, and therefore we're good. Okay, that's fine. You're welcome to do that. You can also just take the derivative of the whole thing and get 1 minus log x over x squared if you do all the derivative stuff, the product rule stuff. And then you'll notice that for x bigger than e, we would have natural log of x bigger than 1, so you can get some stuff so it's eventually decreasing and you can move on and you're fine with all that stuff. And okay, cool, that's neat. But the decreasing thing is a little harder to prove for this one. But really, to me, I just look at the top as natural log is getting small. But it's getting small, but rather natural log of n is getting big, nowhere near as fast as n is getting big, so obviously the thing's decreasing. If you want to be technical about it, then it's a whole thing. You've got to take the derivative and do all that stuff, but I don't want to go with that. All right. So I want to look at the conditions here, and then I'm just going to point to an error estimate and move on with my life. But 59 here is, you want to show that, is it decreasing? Do you think that this is decreasing? So that's the first question, is it decreasing? Yeah, because 1 over n plus 1, the next thing squared, is less than or equal to 1 over n squared. We've done this a lot. We've already done several examples like that. And then the other one is the limit equal to 0? Well, clearly the limit as n goes to infinity of 1 over n squared is 0. Clearly they're both good. And so then series converges by the alternating series test. Of course, this is just an alternator strapped to a geometric series. So there we go. There is a way to do the error estimate here. For an alternating series test, your error here is going to be less than or equal to the n plus 1th term, where r sub n is the remainder after n terms. And we can go through and do some of these. It takes a little while to do that. We can get to figure out that the 3-term approximation is about 5/6. That is, we're just going to use s sub 3. And then we're going to compute some other stuff and go through it. But I'm going to be completely honest with you guys. You've looked at this, and that's enough for me. We don't need to worry about the error estimate on this. You can look at some other stuff where the error is less than some other stuff. You're going to need about 100 terms in this. It just ends up being using a little inequality and then just guessing and checking to figure out when 1 plus n over 1 is less than 1 over 100. Okay, cool. This isn't anything that's going to show up on your test. Error approximation is something that shows up in later classes, especially in engineering majors, but it's so comically easy by then that honestly I only have so much breath left, and it's really not worth their time to look at that. So You can estimate that to within an error. I want you to know that that's something that can be done, and it would take another 15 minutes to explain it, and you'd be fine. If you really want to know how to do errors, especially on alternating series, please, by all means, look it up, but I do not want to do these. So this problem set had us doing these. I don't want to do it. I want to finally get to my favorite test, and we're almost done, by the way, the ratio and the root test, and then we're done with this bad boy. The ratio test is my favorite test because it works on so many things, and it's easy to remember how to do, and you don't have to pick anything to compare it with, and you don't have to be clever, and it just works, okay? It works like this. If you have some series, remember, you're given this, then you just add a +1 everywhere there's an n, and you divide it by the original thing. You take the limit as n goes to infinity in absolute value, and it'll tell you whether it converges absolutely, it diverges, or the test is inconclusive. If you get 1 out, you're up the creek. If you get that L is less than 1, then it converges absolutely. It converges absolutely because it converges and there's absolute values involved. That's all that means. By the way, if something converges absolutely, then it converges. So figuring out that something converges inside absolute value means that it also converges, period. Which is why we could use that test earlier when we were trying to figure out. We could use that divergence test earlier on that alternating series about 4 or 5 examples ago. That's why that was the case. But if something converges absolutely, it converges. If L is greater than 1 or infinity, it diverges. Otherwise, it's inconclusive. Let me show you how to use this because it's the easiest way to do it. We're going to apply the ratio test to this bad boy. So this guy right here, n factorial over 3 to the n, is a sub n. Now, I want you to remember, this is important to remember this, n factorial is equal to n times the next number down, times the next number down, so on and so forth, until you get down to 1. Okay? So, here's how we're going to work with this. And another thing to look at, by the way, is that n plus 1 factorial is going to be, by definition, you're going to start with n plus 1 instead, and then you're going to multiply, think about this, n times n minus 1, so on and so forth. That is, n plus 1 times n factorial. If you don't believe me, just write all this stuff instead of that, and that will still be true. Okay? You can also write n factorial equals n times n minus 1 factorial. That's also going to be true. If you don't believe me, n minus 1 factorial is n minus 1 times n minus 2 times all the numbers down to 1, which is the rest of this stuff here. Right? That's all that is. And then, of course, this n is this. If you don't believe me. If you need a review on how factorials work, there's a billion of them on the internet. Look them up. All right? You need to know how that works. You also need to know how powers work here. So 3 to the n is equal to 3 times 3 to the n minus 1. You can just, when you multiply like bases, you add exponents. Okay? 3 to the n plus 1 is 3 times 3 to the n. Okay? You need to know how exponents and factorials work in order for this to work. But once you know that, this is really easy. We're going to compute L to do the ratio test. So it's equal to the absolute value of, I love this, a to the n plus 1 is we're going to take a to the n and we're going to put plus 1s in it. So a to the n goes on the bottom. So I'm just going to copy that on the bottom. N factorial over 3 to the n. But on the top, everywhere there's an n, I'm instead going to put n plus 1. So n plus 1 factorial over 3 to the n plus 1. Okay? The thing that we're doing with the ratio test is trying to find terms that look like this in the plus 1 term. So watch this. It's equal to the absolute value of, okay, I'm going to keep change flip. So the top is going to keep the same, and it's going to become n plus 1 factorial, okay, over 3 to the n plus 1. Times, keep change flip. Change to a multiplication, and then flip the denominator. Reciprocate the denominator. N factorial. Neat. Cool. That's amazing. Now, what are we going to do with that? Okay, watch this. Watch this. I'm going to say, isn't this just n plus 1 times n factorial. And isn't this thing down here, I'm just going to use both of the facts that we've already written. Isn't this just 3 times 3 to the n? That's the first term. And then I'm going to write the second term again, exactly as it was. Isn't that true? It is true. What happens? This is on the top, this is on the bottom, this is on the bottom, this is on the top. This is n plus 1 over 3. Okay? Now remember, the limit was, of course, we were taking the limit as n approaches infinity. So we're taking the limit as n approaches infinity. So we're taking the limit as n approaches infinity. So then this is just going to be equal to the limit as n approaches infinity, the absolute value of n plus 1 over 3, which is infinity. Clearly, I'm going to plug in infinitely large numbers up here, but the bottom static, this is going to go to infinity. So what can we say? Scroll up. If L is greater than 1 or equals infinity, then it diverges. This is the case that we've got. So the series diverges. So we can say, therefore, the series diverges by the ratio test. I call it the rat test. The ratio test. And if you want to add in a with L equals infinity, you're more than welcome to, but you don't have to. Okay? That's how to use the ratio test. Let's do another one. I love these. Okay? Ratio test to this bad boy. We're going to look at L equals the limit as n goes to infinity of the absolute value of. On the bottom, we just copy and paste 2 to the n over n factorial. Okay? On the top, we don't copy and paste. We add 1 everywhere there's an n. Okay? That's what we're figuring out. Let's figure that out. So we're going to keep, change, flip. And I'm also going to go ahead and separate these out. Watch this. This is 2 times 2 to the n over n plus 1 times n factorial times, and then I'm going to flip the bottom because that's how you divide by division. So n factorial over 2 to the n. That cancels with that. That cancels with that. This is 2 over n plus 1. Remember to copy your limit over. So this is the limit as n goes to infinity of 2 over n plus 1, which equals 0. What does that mean? Well, let's scroll back up. If the limit is less than 1, the series converges absolutely. Therefore, it converges. So that's what we get here. So we can say the series converges. I do this. Converges absolutely. I just put some absolute value signs around it. But you can write out converges absolutely by rat test. By the ratio test. With, we can say L equals 0. That's the answer. And then the scratch work lets me give you all of the points for it. That's how to do the ratio test. Now, pause and try this one. Pause and try it. Pause and try it. Pause it and try it. All right, let's move on. The limit as n goes to infinity of the absolute value of. On the bottom, we have n cubed over 5 to the n. On the top, we have n plus 1 cubed over 5 to the n plus 1. Okay? This is going to equal the limit as n approaches infinity. Remember, all of this is big L. The absolute value of, still, n plus 1 cubed over 5 to the n plus 1 times 5 to the n over n cubed. Okay? This equals the limit as n goes to infinity of, okay, and on the bottom I need to write this as 5 times 5 to the n. So that it'll cancel with this 5 to the n up here. This n plus 1 cubed, however, is going to have to get FOILed out, unfortunately. So I'm going to multiply n plus 1 times n plus 1 times n plus 1. And I'm going to see what that turns into. So let's see here. N plus 1 times n plus 1 times n plus 1 is going to end up giving us Can we think about this differently? I might be able to think about this differently. Because that would be a 5n cubed. Let me see. I could FOIL this out and then cancel the largest terms and talk about it that way. Maybe I can get away with doing this another way. Let me try to be a little bit lazier on this. Pragmatic, let's say. That's being lazy with a purpose. I know that's going to cancel with that. So then this is going to be the limit as n goes to infinity of... Oh yeah, this is going to be 1/5, basically. 1/5. N plus 1 over... Yeah, obviously. This is going to be 1/5 n plus 1 over n, all cubed. Still an absolute value there at the edge of the screen. And we know... we know what happens to this guy as n goes to infinity. It goes to 1. So we know that then the limit is equal to 1/5. Because we know that this effectively doesn't matter as n gets big. Those cancel. 1 cubed is 1. This is just 1/5. The whole thing's just 1/5. So what do we know about that? Well, scroll back up. 1/5... Let's see here. 1/5 isn't bigger than 1. Oh, 1/5 is less than 1. So then the series converges absolutely. That's all that you need. So the series converges absolutely. So we say series converges. Okay. And you can say absolutely if you want to do like that. Converges absolutely by rat test. Do you want to say with L equals 1/5? That's fine. Specifically, you want to say, maybe you want to say that 1/5 is less than 1. Maybe you want to say that on that. That might be smart. Right? You say that equals 0, right? You say equals 0, which is less than 1. Right? It's less than 1. Right? It's less than 1. So maybe that's what you want to say. You want to say equals infinity. Well, that just equals infinity. Maybe that's fine too to put in there. Okay. Let's look at this one. This one's a fun one. This one's one that you got to get a little weird on, but it's possible. And I love putting this one on a test, by the way. Hint, hint. So we want to do L equals the limit as n goes to infinity of the absolute value of... On the bottom goes this guy. Just like this. On the top goes the same guy, except everywhere there's an n plus 1 now. So it's going to be n plus 1 to the n plus 1. I love this one, okay? So this is going to be the limit as n goes to infinity of... And then I'm just going to keep change flip, and I'm not going to... Well, I can do a little bit more, but I can't do a ton more. Right, so watch this. I can do the n plus 1 times n factorial over n plus 1 to the n plus 1, I guess. But I'm going to multiply that by, and then I'm going to flip this to be n to the n over n factorial. And then I'm going to put that on there. I'm going to notice that that cancels with that. And then I'm going to come on down here, and I'm going to write the limit as n. Keep carrying your limits. And then I'm going to write this. Watch this. This is n plus 1. Okay. There's a bunch of ways to go about this at this point. Over n plus 1 to the n plus 1 times just n to the n. Now, notice, please notice this, how a copy of this guy is sitting up here. If I pull out one of these n plus 1s, these will cancel. So I'm going to do that. That is, I'm going to use the fact that, let me write this in blue, I'm going to use the fact that n plus 1 to the n plus 1 power, I'm going to pull out one copy of n plus 1 right there. And so how many other copies of n plus 1 are left? Well, n. So I'm going to use this fact to write this like that instead. And when I do that, this n plus 1 will cancel with this n plus 1, and I'll be left with just n plus 1 to the n. So then this will equal, still in blue, n equals, limit as n goes to infinity of the absolute value of, and then I'm just going to write all that out, and that's going to be n to the n. It's going to go on top. I'm just going to write that on top now. It was a 1 because it canceled. Over, and then n plus 1 to the n. Okay? Okay. Now these are both raised to the n power, so I can write them together inside a single thing. Limit as n goes to infinity of, limit as n goes to infinity of the absolute value of, what's this? This will be n over n plus 1 to the n. Okay, I love this example. I love this example because this guy right here, you might notice, is the reciprocal of n plus 1 over n. N plus 1 divided by n to the nth power as n goes to infinity is e. Therefore, this integral is going to equal 1 over e. Which is so cool. That's so cool. Because you can, look here, just divide that by n, divide the numerator by n, and then divide both terms of the denominator by n. And you'll get 1 over 1 plus 1 over n all to the n. And that'll give you 1 over e in the limit. In the limit, I guess I can write like that. But you'll notice that 1 over e is specifically less than 1. Therefore, this is going to converge. Series converges, okay, absolutely by the rat test. And if you want to say with L equals 1 over E, you can. But that's so cool. And that's just being able to recognize some facts about how you want to simplify that. Just divide everything in that thing by, just divide everything in that term by n, and you'll be good. I keep jumping around on this thing because I click in the wrong place and then it takes me down here and it's kind of annoying. But anyway, the root test is divided into a couple of parts here, and it line broke badly. But what we're going to do this time for the root test, and this is the last part of the example, by the way, is we're just going to contribute our L this way. The limit as n goes to infinity of the nth root of the absolute value of your thing, of your summand there. And then you're going to look at the exact same criterion as the ratio test. If it's less than 1, it converges. If it's greater than 1 or it equals infinity, it diverges. And if it equals 1, the test is inconclusive. The only time to use the root test is if you have nth powers on the outside like this. It's the only time to use the root test, because that is what the nth root of something, this guy right here, the nth root of something is going to undo that nth power. It's the only time to ever use the root test. Use the root test when you have powers of n on the whole thing. So for this one, for the root test, we're going to use L equals, okay, and it's the limit as n goes to infinity of the nth root of the absolute value of this guy. Now look, n is going to infinity and it starts at 1. 3n is always going to be positive. 2n plus 1 is always going to be positive. N's always going to be positive. This is always going to be positive. So I don't care about the absolute value. So I don't have to write it. Even though it's in the actual definition, I don't have to write it because everything's going to be positive regardless. Okay? Well, look here. The nth root of the nth power of something is going to do that. And then I'm going to get the limit as n goes to infinity of... Normally you would have to look at this in terms of absolute value, but we don't actually care this time. If you want to write the absolute value signs, be my guest. You just don't have to, is what I'm saying, in this case. This, as n gets big, this doesn't matter. The n's cancel. This is going to be 3/2. If you want to do it mathematically, again, divide every term in the top and the bottom by n, and you'll get to the same place. This is 3/2. What can we say? 3/2 is bigger than 1, therefore the series diverges. That's what we can say. So this is bigger than 1, so we say series diverges. There's no such thing as absolute divergence, by the way, by the root test. You want to say with L equals 3/2? Fine. The more information you give me, the better, but you don't have to. Okay? That's how you do the root test. Let's do another one. These are all really easy. You see an nth power on the outside, use the root test. Otherwise, don't use the root test. That's it. L, or if it says to use the root test, I guess use the root test. But L, the limit as n goes to infinity of the nth root of, okay. Now, n plus 1, we start at 1 and we go to infinity. N plus 1 is always going to be positive. 2n's always going to be positive. N's always going to be positive. I don't have to write the absolute values. Otherwise, I do. But I'm not going to because I don't have to. N plus 1 over 2 to the n. You're never going to believe this. These cancel. And then we're going to look at this, and it's going to end up being a half. Look at this. Limit as n approaches infinity of n plus 1 over 2n. As n gets big, essentially the plus 1 doesn't matter. We only care about the highest degree things that both happen to be 1. So these both cancel. You get 1 over 2, okay, which is less than 1. Therefore, this thing converges. So we say the series converges absolutely by root test. Root, capitalize it, root test with L equals a half, which is less than 1, which is fine. That's all that we need. Okay, putting this less than 1 on here helps a lot, by the way. So that's it. Yeah. For both of these tests, the values of L determines the result. Okay, we can go through and we can state the conclusion on a bunch of these, and we can look at a bunch of this sort of stuff. And then we could look at some of the strategy guides and stuff. And I do want to look at a strategy guide and just look over it more generally. But I think that example 69 here it's a nice example to end on. So let's apply the root test to this guy. So we're going to do L equals the limit as n goes to infinity of the nth root of 5/4, guys. You're not going to believe is always going to be positive. So 5/4 to the nth power. These are going to cancel, and this is just going to be 5/4 in the limit, which you might notice is going to be bigger than 1. So therefore, this whole thing is going to diverge. So therefore, the series diverges by root test. Okay. Now there's more examples in here that I could go over, but I'm going to be honest, my voice is about to go out. And I do want to get and talk to a few more things real quick. So for both tests, the value of L determines the limit. We can do these really quickly. L is 2/3. That's less than 1. It converges. L is 5/4. That's greater than 1. It diverges. L is 1. We can't say anything if it equals 1. So we can't say anything. We've got to use another test. Ratio test and root test fail us horribly if L equals 1. Hope it never does. Okay. In some cases, we can get 1. Another test has to be used. We could show that it's inconclusive for this. If you go through and do the math, you can see that it's inconclusive. You'll get L equals 1. You'll get L equals 1 for this as well. For both of these, you use a different test. These are both p-series. Use the p-series. This diverges because n equals 1, or because p equals 1, rather. It also diverges because it's the harmonic series. This, however, is going to converge because p is greater than 1. So you're fine on that one. But the root test won't work for it either. The root test won't work for it because it's a bad test to use anyway. The ratio test or root test is more natural. Which one's more natural for this? Which one do you think? The root test, that's right. Because there is an nth power on here, the root test is going to work a lot better. It's going to get rid of that. You're going to get 2/3 in your limit. You're going to see that that's less than 1. And like we've said all the way up here, it's less than 1, so it's going to converge. That's cool. That's all that you're doing in this. So I'm going to scroll through this. I'm going to leave this to you to look at case by case. And I want you to pause the video. I want you to give these a good shot. And I'm just going to go through these and give you the answers as I move on. All right? As a strategy guide to test any series, check to see if the limit of an, check that limit. If the limit isn't 0, it diverges. Otherwise, see if it is geometric or a p-series or whatever, and then do the appropriate test. If it's a geometric series, you know what to look at. If it's a p-series, you know what to look at. If it alternates, look at the alternating series test. If it has a bunch of factorials and powers of n in it, that's a ratio test. If it has everything to the power of n, that's a root test. Otherwise, you're stuck with one of the two comparison tests. I would always try the limit comparison test first because it's easier. And that's it. That's the strategy guide always. So, for this guy here, what's the first test that you would apply? Trick question. The first test should always be the divergence test. And if you do the divergence test on this, you'll get that it's 1. That's not 0, therefore it diverges. This guy here, example 77. For that series, what type of series is it? It's a geometric series because it looks like AR to the n. Specifically, the ratio for this one, assuming it starts at 0, is 1/2. It'll be 1/2 if it starts at 1, but A would be 1/2 in that case, and I'll let you convince yourself why that's true. Example 78. What's the most appropriate test? The signs alternate. There's an alternator. Use the alternating series test. That's a pretty easy one. How about this one? This one here, the test should probably be the root test. Okay. In general, by the way, there's some cool stuff here. This line broke really weird in my LaTeX, but ignore that. If you have factorials or exponentials everywhere, use the ratio test. If you have powers of your n is on the bottom, use the p-series or a comparison test. Okay. If you have alternating signs, use the alternating series test, obviously, assuming it's decreasing. And if you have logarithms, that's the only time you're going to want to use the integral test. Otherwise, it'll be a comparison test. You never actually have to use the integral test, by the way. There's always another way to do it. Well, almost always another way to do it, and there certainly will be on your test. What's the best test for this? It's the ratio test, because there's an exponential, there's a factorial and an exponential. Cool. What's the best test for this guy, number 80? Well, 1 over n log n has a standard integral. We've done it before. It's the integral test. How about this guy? It alternates, so it's the alternating series test. How about this guy? 2 to the n plus 1 over n cubed. What do you think about him? How are you going to do example 82 there? I would try the comparison test. You could try the limit comparison test as well. I would try comparing against, look at just the degrees of the top, the maximum degrees of the top, 2n over n cubed. So that's going to give us 1 over n squared when you reduce that. I would compare against n squared. We know 1 over n squared. I know that 1 over n squared converges, so I would try the comparison test where it converges. That is, you put the convergent thing on the outside of the comparison, and you put this on the inside, and you see if it works out. And if you need to compare a little bit, well, chuck a 2 on it, and that'll do it for you. If a test doesn't work, try a different method, right? If the ratio test gives L equals 1, right, it's inconclusive, so you should try a different test. Try the comparison test, the root test, the integral test, alternating series test, or the p-series test. It might be a geometric series. Who knows? And then if the divergence test gives 0, you can conclude you've got to move on. And that, ladies and gentlemen, is the end.